Hello there, and welcome to the Sleepless Scientist, a quiet corner of the cosmos where your thoughts can loosen and curiosity drifts softly into calm. Tonight, we'll be exploring one of the deepest, most haunting questions ever asked. How did the universe create itself? How did everything, from stars to atoms, from gravity to consciousness, arise from nothing at all? And if there truly was nothing, how could it have known to begin? These are not just scientific puzzles, but quiet invitations to wonder, echoes from the beginning that still hum beneath every breath you take. But before we start our slow journey through time and mystery, I'd love if you could take a moment to like this video and subscribe. Only if these calm explorations bring you peace. And when you're ready, leave a comment to tell me where in the world you're listening from and what time it is for you right now. It's always such a quiet joy to see how far this little constellation of night thinkers reaches, each of us shining softly in our own corner of time. Now, dim the lights, maybe let a gentle hum or the rhythm of your breathing fill the room. And if your mind begins to drift as we explore the origins of everything, that's perfectly fine. Let it wander, we'll still be here, unfolding the story of how existence itself learned to begin. Imagine for a moment that you are lying under a night sky. It stretches endlessly above you, sprinkled with countless stars. Some shine fiercely, others faintly. Some are so dim you can only see them if you avert your gaze slightly, letting the corner of your vision catch what your direct stare cannot. The stars seem eternal, but every point of light has its own story. A birth, a middle age, and one day, a fading. Beneath that tapestry of stars, it is natural to wonder, did all of this always exist? Or did it begin in a single moment, when nothing turned into something? For most of human history, the universe was imagined as eternal and unchanging, a grand stage set once and for all. But in the last century, telescopes and mathematics have whispered a different tale. They have told us that the universe is expanding, that galaxies drift apart like leaves scattered across a pond. They have revealed a soft glow, invisible to the eye but recorded by careful instruments, a glow that pervades all of space equally. They have shown us that the simplest atoms, forged in the first few minutes, still trace their pattern across the cosmos, and they have mapped the vast web of galaxies, filaments, and voids, the grand structure of cosmic architecture. These are the four great pillars that support our modern understanding of the universe's beginning. The expansion discovered by Hubble, the faint background glow of the cosmic microwave background, the primordial recipe of light elements, and the large-scale structure of galaxies spread through space. Together they are like four voices humming the same song, a song that tells of a hot, dense origin, a beginning we call the Big Bang. But even as we call it that, we must be gentle with words. The Big Bang was not an explosion in space. It was not firecrackers bursting into emptiness. Instead, it was space itself stretching, the very fabric enlarging, carrying matter and light along with it. Imagine bread dough rising, each raisin drifting away from the others, not because the raisins move, but because the dough itself swells. Imagine the soft surface of a balloon inflating, each painted dot receding from every other dot, no matter where you stand. This is the story told not by myth or poetry, but by the faint signals written into the night sky, signals we have only recently learned to read. As we move forward in our exploration tonight, we will trace the universe's story step by gentle step, from the fog of its earliest instance to the quiet expansion we observe now. We will speak of moments so brief they defy imagination, trillionths of a second when space inflated faster than light, smoothing wrinkles, stretching tiny quantum ripples into the seeds of galaxies. We will drift through a hot broth of particles, where matter gained the slightest edge over antimatter. We will pause in the minutes when helium and deuterium formed, a cosmic recipe still present in the air we breathe today, and we will listen to the echo of photons released when the universe became transparent, an afterglow still humming all around us as the cosmic microwave background. Each stage of the story can sound impossibly technical when recited in equations and constants. But here, we will soften the edges. We will let the Planck era be a foggy dawn, where laws of physics blur. We will let inflation be the sudden rising of dough, the ironing out of creases. We will let recombination be a curtain lifting, revealing a glow across the sky. And we will let dark energy, that quiet hand pulling galaxies apart, be like a faint wind spreading leaves across a courtyard. There are puzzles still unsolved, of course. Why did inflation begin, and what ended it? Why is the universe's expansion accelerating, as if pushed by an invisible pressure? Why does theory predict a vacuum energy 100 orders larger than what we see? These are not questions we will rush to solve, but mysteries we will hold softly, like shells picked up along a shore, listening to the whispers inside. And because this is not only the story of physics, but the story of life, we will eventually ask, if the cosmos so naturally creates galaxies and stars, if it forms planets and oceans, why does the night seem so silent? Why, in the great depth of the universe, do we not yet hear other voices? This too will be part of our journey, the paradox of silence in a cosmos so fertile. For now, let us begin at the beginning, or rather, before the beginning. For the tale of how the universe created itself starts not with blazing light, but with a stillness, a silence, a place where the rules of space and time had not yet congealed. It begins with the question of nothing, and whether nothing is ever truly empty. The story of the universe's expansion begins not with a bang in the way fireworks burst against a night sky, but with a gentle realization, one that dawned slowly on human thought. For centuries the heavens were believed to be fixed, stars set in a crystalline sphere, planets wandering but still bound within a perfect eternal dome. Even when telescopes began to show nebulae and faint smudges, few imagined that these were other galaxies, much less that all of them were in motion, drifting apart in a cosmic dance too vast to feel. The shift came with light and with patience. When astronomers studied the faint glow of galaxies beyond our own, they saw that the light was shifted toward the red end of the spectrum. It was as if every galaxy were quietly humming a deeper note than expected. Its song stretched out, slowed down. This was not just one or two galaxies, but almost all of them, and the farther away a galaxy was, the greater the shift. Edwin Hubble, working in the late 1920s, recognized the pattern. The universe was expanding. Think of light as a kind of music, each wave a note. When space itself stretches, those notes are pulled apart, their pitch lowered. It is not that galaxies are racing through space like cars down a highway, but that the very highway itself is lengthening, carrying the cars apart whether they move or not. Imagine you had raisins sprinkled in dough. As the dough rises, each raisin drifts away from the others. No raisin is special, no raisin is the centre. The expansion is everywhere at once. This is one of the most difficult, and at the same time most beautiful, truths to hold in mind. Every point of the universe is expanding away from every other point. There is no central hub, no edge, no outer shell. If you imagine standing anywhere in the cosmos, you would see galaxies receding in all directions as though you stood at the centre, and yet everyone else standing on their own distant shore would see exactly the same thing. The universe makes each of us feel central, even while reminding us that we are not. The redshift that Hubble and others measured became the first great pillar of the Big Bang picture. If space is expanding today, then yesterday it must have been smaller, the day before smaller still. Roll the story backward and the galaxies converge. Their light grows bluer and hotter, the distances collapse, and what is now vast and cool becomes crowded and fiery. The universe as we see it implies that in the deep past, everything was compressed into a hot, dense state, a place where ordinary intuition falters. To explain this expansion, cosmologists turn to the equations of general relativity, the framework Einstein had built just a decade earlier. These equations describe space and time not as a static backdrop, but as a fabric that bends and flexes in response to energy and matter. In the same way that a sheet stretches under the weight of a heavy ball, space stretches under the influence of cosmic content. The solutions found by Friedman, Lemaitre, and later others showed that an expanding universe was not only possible, but in many ways unavoidable. A static universe, Einstein's original hope, turned out to be unstable. The mathematics suggested a cosmos either growing or shrinking. Observation settled the matter, it was growing. At first, this was difficult for people to accept. Sir Arthur Eddington, a leading astrophysicist, said he found the idea of a beginning repugnant. Others dismissed Lemaitre's notion of a primeval atom as theological intrusion. But as evidence grew, resistance softened. What had once seemed unthinkable became the new normal. The universe had not always been the way it is. It had changed, and was still changing. There is something humbling about this discovery. When you look up at the night sky, it feels timeless. Stars shine steadily, planets follow familiar paths, constellations trace the same patterns seen by our ancestors. And yet beneath that stillness is a slow unfolding, galaxies receding like petals, opening in a flower too large to grasp. You and I cannot feel it, any more than a fish can feel the ocean's tides in each moment, but the expansion is real and all-encompassing. An expansion is not uniform in how we perceive it. The farther a galaxy lies, the faster it seems to recede. This is not because of a peculiar speed it chose, but because space stretches more between us and it. Beyond a certain distance, galaxies recede faster than light, not because they violate relativity, but because relativity allows space itself to expand without limit. This is another subtle truth. You can never catch up with a horizon that itself is running away. The light from certain galaxies emitted today will never reach us. The universe is not only expanding, it is drawing curtains across parts of its own stage. Still, expansion alone was not proof of a fiery beginning. It was one voice in a choir that needed harmony. The cosmic microwave background, the light elements, and the web of galaxies would eventually join it. But Hubble's law was the first, the foundational rhythm that turned the eternal stage into a story with motion, a play with a beginning and perhaps an end. Think of it this way. When you blow air into a balloon, you see the surface stretch. If you painted little dots across the rubber, they would all move apart as the balloon swelled. To each dot, it looks as though all others are retreating. None sees the centre, for the centre is not on the surface at all, but outside their world. Our universe is like that, an expansion not on a stage, but of the stage itself. There are, of course, questions left dangling. Why does the universe expand at the rate it does and not faster or slower? What determines its curve, flat, open, or closed? How do we measure these things when we can never step outside and look back? These puzzles will guide our journey forward. For now, it is enough to rest in the thought that the universe breathes. It stretches and grows, and in its quiet expansion lies the key to its history. If we follow the universe's expansion backward, rolling the film of cosmic history in reverse, galaxies draw closer, stars vanish into haze, atoms dissolve into plasma, and the glow of the cosmic background collapses into an opaque fog. Continue further still, and even protons and neutrons lose their identities, melting back into quarks and gluons. Keep going, and after just a few steps on the logarithmic staircase of time, we reach an interval so small, so utterly unlike anything in daily experience, that even our best equations stop speaking. This is the Planck era, the first whisper of the cosmos, a span that lasted only until about 10 to the negative 43rd seconds after the beginning. To pause here is to stand before a horizon of knowledge. 10 to the negative 43 seconds, 43 zeros tucked behind the decimal point, marks the limit where our theories fail. Beyond this, gravity is expected to be quantum in nature, woven not as a smooth fabric, but as something granular, perhaps foamy, jittering with uncertainty. Yet no completed theory of quantum gravity exists. The Planck time is therefore a boundary line, a fog bank into which our mathematical ships cannot sail. We can stand on the shore and we can guess what lies within, but the waters themselves remain hidden. It is tempting to picture the beginning as a singular point, a dot exploding into everything. But this image misleads. The Big Bang was not an explosion in space. It was the expansion of space. And the singularity often spoken of in textbooks is not a physical thing, but a signal that the mathematics has broken down, like a compass needle spinning when brought too close to a magnet. We should not imagine the singularity as a little ball waiting to burst. Rather, we can think of it as a boundary where our current language ends. In this earliest instant, temperatures soared beyond what words like hot can capture. Energy densities reached values so large that any attempt to picture them slips from our grasp. Time itself may not have flowed in the way we know. The very distinction between before and after may not have applied. Imagine standing in a room filled with mist so dense you cannot see shapes, cannot even tell where the walls are. That is the Planck era, a silence so deep our equations cannot enter. And yet, out of this silence, something stirred. We do not know if the universe began from absolute nothing, or from a prior state. Perhaps a cycle of expansions and contractions, or perhaps a quantum fluctuation in a timeless sea. We do not know if space and time themselves were born here, or only transformed. But what we do know is that within a tiny fraction of a second, the fog cleared just enough for new patterns to form. The Planck scale is not only a time, it is also a length and an energy. The Planck length, about 10 to the negative 35th power meters, is the smallest scale where the smoothness of space-time is expected to fail. Below this, the concept of a distance itself may lose meaning. Imagine trying to paint with a brush so coarse that no matter how fine a detail you attempt, it blurs into fuzz. That is how nature treats the Planck length. The Planck energy, likewise, is so immense that our most powerful particle accelerators are laughably small in comparison, like toy windmills compared to hurricanes. These scales are reminders that our physical laws, so successful in the everyday world and even in stars, have limits. Still, physicists explore possibilities. Some imagine space-time as a network of tiny loops, woven like a fabric at the Planck scale, a theory called loop quantum gravity. Others picture it as strings vibrating in higher dimensions, their harmonics producing the particles and forces we see. Some imagine foam, where microscopic bubbles of space-time pop and reform endlessly. None of these ideas has yet crossed from speculation into proof, but each is a lantern held up to the fog, searching for glimmers of truth. Why linger on a place we cannot see? Because the character of this first moment matters. If the universe began with a singularity, then perhaps time itself had an edge, and the question of before becomes meaningless. If instead the singularity is avoided, replaced by a bounce or a quantum transition, then the universe may have a past stretching infinitely behind us. The Planck era is the fork in the road where these possibilities diverge. For our story tonight, though, we need not resolve the puzzle. It's enough to know that the earliest moment was not an explosion in space, but a boundary where known physics stops. The Planck era whispers to us of limits, of mysteries not yet solved. It reminds us that beginnings are often not sharp points, but hazy transitions where old frameworks dissolve and new ones are born. As you imagine this, you might let your mind drift to the quiet before dawn, when the world is still and even birds hesitate to sing. The Planck era is like that, a pause before the great unfolding, a silence holding within it the possibility of sound, light, and form. Out of this silence, the next chapter of the universe began, a sudden swelling, a breath of expansion faster than light, smoothing, stretching, and setting the stage for all to come. From the fog of the Planck era, where the language of physics dissolves into silence, the universe seems to have drawn in a great breath. What followed was not merely expansion as we observe today, but an expansion so sudden, so swift, that ordinary words stumble in its wake. We call it cosmic inflation, a name that suggests balloons and airy swelling, but which in reality was a surge of space itself, an enlargement faster than light could ever hope to chase. This idea did not arise from fancy alone. It was born of puzzles, quiet contradictions, in the universe's story that refused to be ignored. The first puzzle is the horizon problem. When we look at the cosmic microwave background, the faint afterglow released hundreds of thousands of years after the beginning, we see that its temperature is nearly uniform across the sky. No matter where we look, the cosmic soup has the same warmth, differing by less than 1 part in 100,000. Yet, if the universe had expanded at a steady pace since the beginning, there would not have been enough time for opposite sides of the cosmos to share information, to smooth out and settle into such harmony. It would be as if two people on opposite sides of an ocean spoke with matching voices, though no message could ever have passed between them. Inflation solves this by shrinking the distance. Before inflation, the regions of the universe were close enough to interact, to whisper to one another. Then came the sudden stretch, carrying those whispers to scales larger than the observable sky. The second puzzle is flatness. When cosmologists measure the geometry of the universe, they find it astonishingly close to flat. Not curved like a sphere or like a saddle, but stretched smooth, as if space were a calm tabletop extending in all directions. Yet, for it to be this flat today, it must have been unimaginably flatter in the beginning. Without some mechanism, the slightest deviation would have grown into a wildly curved universe, collapsing too quickly or tearing itself apart. Inflation explains this too. Just as a balloon smoothed out loses wrinkles when blown large, so inflation ironed the creases of space-time, pressing it toward flatness. The third puzzle is more obscure, the problem of relics, magnetic monopoles and other exotic particles predicted by high-energy theories. If the early universe had expanded steadily without inflation, such relics should be everywhere, cluttering the cosmos with their presence. But we do not see them. Inflation dilutes them away, scattering any oddities across volumes so vast that their density becomes negligible. Like a drop of dye poured into an ocean, their trace vanishes into immensity. And so inflation was proposed, not as decoration, but as an answer to these riddles. A short burst, lasting from about 10 to the negative 37th to 10 to the negative 32nd seconds, was enough to stretch the universe by a factor so immense it defies ordinary intuition. Imagine something smaller than a proton swelling to the size of a visible apple in less than a heartbeat. Imagine every crease in a sheet of paper smoothed flat in an instant. That was inflation, a breath faster than light. Within this expansion, another miracle occurred. The quantum jitters of the vacuum, tiny fluctuations always bubbling beneath reality, were magnified to cosmic proportions. These fluctuations, normally confined to the subatomic realm, were stretched until they painted the scaffolding of galaxies. regions slightly denser than average pulled in more matter grew into clusters, while slightly emptier patches became voids. The entire architecture of stars and planets, of galaxies and superclusters, was seeded by random tremors in the fabric of space. From quantum uncertainty came the grand design of the night sky. We can still see the fingerprints of these fluctuations today. The cosmic microwave background is mottled with faint speckles, slight variations in temperature that mirror the early seeds. These variations match the predictions of inflation almost perfectly. Nearly scale-invariant Gaussian ripples, with just the tiniest tilt that tells us they are not uniform but close. It is as though inflation left behind a faint watermark, a signature confirming its breath. And yet, mysteries linger. Inflation requires a field, often imagined as the inflaton, whose energy drove the rapid swelling and then decayed to reheat the universe. But what this field truly was, or why it took the values it did, remains uncertain. Some models require delicate tuning, like balancing a pencil on its tip, to ensure just enough inflation but not too much. Others raise questions about what happens at scales beyond the Planck length, whether inflation ever truly ends, or whether it leads to eternal inflation, where some regions stop expanding and form universes, while others swell forever, birthing a multiverse of possibilities. Physicists continue to search for evidence. One hope lies in primordial gravitational waves, faint ripples in space-time that inflation might have generated. These would leave a swirling pattern, called B-modes, in the polarization of the cosmic microwave background. Experiments such as BICEP and the Keck array strain to detect these whispers, but so far the universe has remained coy, revealing nothing decisive. Perhaps one day we will hear the echo of inflation directly in the trembling of space-time. Until then, the evidence remains indirect but persuasive, like footprints leading into fog. For our purposes tonight, inflation is not only a mechanism but a metaphor. It is the universe ironing itself smooth, like cloth pulled tight, like dough rising until it erases every crease. It is randomness lifted into permanence, noise woven into the blueprint of galaxies. It is the astonishing truth that the great sweep of stars owes its form to the tiniest, most uncertain jitters of nothingness. As you let these ideas settle, you might imagine your own breath slow and steady expanding your lungs. The universe too breathed once, in a way so sudden and vast it set the course of all that followed. And just as every exhale leaves a trace in the world around you, that primordial breath left a trace in the galaxies, in the background glow, in the very fact that you exist tonight to wonder about it. When the breath of inflation ended, the universe did not simply stop stretching and remain empty. Instead, all the energy that had driven that sudden swelling poured back into the cosmos, igniting it with particles and light. This transition is called reheating, though the word feels almost too gentle for what happened. It was not the warming of a room after a cold night, but more like a furnace being stoked with unimaginable intensity. What had been a nearly empty, stretched out space was suddenly filled with a storm of creation. In this storm, particles emerged in a flood. Quarks and gluons swirled together in a dense plasma, a kind of hot broth so thick with energy that ordinary matter could not yet take shape. Imagine a pot of soup boiling so furiously that no distinct ingredients can be seen, only a blur of motion and heat. That was the early universe in its first microseconds, a quark-gluon plasma, opaque and chaotic yet full of potential. This broth was no ordinary soup. The forces of nature themselves were still sorting out their roles. At higher energies, the distinctions between forces blur, and only as the universe cooled did they begin to separate, like colours spreading from a single light. The strong force took hold of the quarks, binding them eventually into protons and neutrons. the electromagnetic force prepared to guide the future interactions of light and charged particles. The weak force determined the rates at which particles transformed into one another, crucial for the balance of matter to come. Gravity, always the most patient of forces, simply shaped the whole stage on which the drama unfolded. Yet within this soup, a puzzle was hiding, one of the greatest mysteries we still face. According to our best understanding, the laws of physics treat matter and antimatter almost like perfect mirror images. When particles collide, they should produce equal amounts of both, and when matter meets antimatter, they annihilate, releasing pure energy. If the universe had followed this rule perfectly, every bit of matter should have been cancelled by antimatter in those first flashes. The result would have been nothing left behind. No stars, no planets, no people. And yet, here we are. Somehow, matter gained a small but decisive advantage. This imbalance is called baryogenesis, the mystery of why the cosmic coin landed ever so slightly in favour of matter. Imagine flipping a coin billions upon billions of times, and though the laws say heads and tails are equal, it lands heads just a hair more often. That tiny bias, perhaps only one extra particle of matter for every billion pairs of matter and antimatter, was enough to tip the scales. Almost everything annihilated, but that slight excess remained. That excess became the atoms that later formed galaxies, oceans, and the breath you're taking now. Physicists search for the reason behind this bias. It may lie in subtle violations of symmetry, in how certain interactions treat matter and antimatter differently. It may involve processes linked to the neutrinos, ghostly particles that pass through you by the trillions every second without leaving a trace. Or it may involve physics we have not yet discovered, laws that reveal themselves only in the extreme conditions of the early universe. For now, the matter-antimatter asymmetry remains one of the deepest questions, a reminder that our existence is balanced on the edge of a cosmic mystery. As the quark soup cooled further, protons and neutrons became stable. They gathered into the first building blocks, ready for the next stage, nuclear fusion during Big Bang nucleosynthesis, which would forge helium, deuterium, and a trace of lithium. But in these earliest microseconds, the universe was still too wild for such structures. Everything was motion, scattering, recombining, a dance of particles in a furnace. And yet, even in this chaos, order was quietly being laid down. The fluctuations seeded during inflation were now embedded in the soup. Regions just slightly denser than average pulled in more matter, their gravity whispering louder. Others, slightly less dense, fell quieter. The stage was being set for the clumping that would one day become galaxies. In this way, the randomness of quantum foam, stretched vast by inflation, began to guide the destiny of stars. It is difficult to picture such a time. No atoms, no light shining freely, no empty spaces. Only a universe packed tighter and hotter than anything we can recreate in laboratories, though particle accelerators have given us fleeting glimpses. In those glimpses, when heavy ions collide and briefly recreate the quark-gluon plasma, detectors capture showers of particles spraying outward. In that moment, we glimpse the broth that once filled everything. When you think of the early universe, perhaps imagine a kitchen, but not a quiet one. Imagine pots boiling over, flames too bright to look at, steam clouding every corner. The broth churns, yet from it will emerge the ingredients of something lasting. The early universe was a kitchen of extremes, and we are the flavour left over, the trace of matter that survived. And so, as reheating poured energy into particles, as quarks swam in their soup, as matter barely gained the upper hand over antimatter, the universe marched forward. It was still only fractions of a second old, yet the seeds of everything were already present. Expansion continued, cooling slowly, carrying the broth into calmer stages. One day, perhaps, we will understand precisely why the coin landed on matter more often than antimatter. For now, it is enough to marvel at the unlikeliness of it. Every star in the sky, every planet, every living thing, all are built from that tiny surplus. Without it, the universe would have been light alone, a blaze without structure, brilliant but barren. Instead, there was just enough imbalance to allow atoms, chemistry, life and minds to arise. As you let that thought settle, you might picture yourself holding a coin, flipping it slowly, watching it spin in the air. Imagine that spin repeated 1 billion times over. Imagine that just once in all those tosses, the coin shows you matter instead of annihilation. That one chance was enough. That one chance is why there is something rather than nothing, why the night sky glows with galaxies, why you are here tonight, listening to the quiet story of the universe. By the time the universe was a single minute old, the quark soup had cooled enough to allow the first real ingredients of matter to take shape. Protons and neutrons, having formed in the cooling broth, were now stable enough to linger. The expansion slowed just enough to permit them to join together, and the cosmos became, in a sense, a kitchen. The cook was not patient, and the stove was not gentle, but in a few minutes of furious activity, the first recipe of the universe was written. This process is called Big Bang nucleosynthesis, and though it sounds technical, its essence is simple. Light nuclei formed from the primordial soup of protons and neutrons. In those minutes, the temperatures hovered around 1 billion degrees, far hotter than the cores of stars, yet falling rapidly as the cosmos stretched. At just the right moment, fusion began. Neutrons paired with protons, creating deuterium, the simplest nucleus beyond hydrogen. Deuterium fused into helium-3 and helium-4. A trace of lithium-7 also emerged, and then the window closed. As the universe continued to expand and cool, conditions drifted away from those required for fusion, and the recipe ended. The result was a mix of ingredients that has remained largely unchanged ever since. About 3/4 hydrogen by mass, about 1/4 helium, and tiny traces of deuterium and lithium. Nothing heavier. The cosmic kitchen had one short cooking session, and then the oven switched off. Heavier elements like carbon, oxygen and iron would have to wait billions of years until stars lit up and took over as forges. What makes this moment remarkable is not only what it created, but how well it matches what we observe today. When astronomers measure the helium abundance in distant galaxies, or the amount of deuterium in clouds of primordial gas, they find nearly perfect agreement with the predictions of Big Bang nucleosynthesis. It is as though a single universal recipe was followed everywhere, once, and its flavour is still detectable across the cosmos. The agreement is one of the strongest confirmations that the Big Bang picture is not just a story, but a reflection of how things truly unfolded. And yet, there is a wrinkle, the so-called lithium problem. The predicted amount of lithium-7 from Big Bang nucleosynthesis is greater than what we actually observe in old stars, where primordial compositions should be preserved. For reasons not yet understood, nature seems to have misplaced some of its lithium. Perhaps it was destroyed in the atmospheres of stars, perhaps new physics played a role in the early minutes, or perhaps our understanding of nuclear reactions at those energies is incomplete. Whatever the answer, the lithium problem remains an open puzzle, a reminder that even recipes handed down by the cosmos can be slightly enigmatic. To make sense of all this, you might imagine the universe as a pot of soup cooling on the stove. At the start, the heat is so great that nothing distinct can form. The ingredients are dissolved in a blur. As it cools, ingredients begin to clump and react, producing new flavours. But the window is narrow. Leave the soup too hot and nothing binds. Let it cool too much, and reactions freeze out. In the early universe, conditions aligned for only a few minutes, just long enough to produce helium and its cousins, before the temperature dropped too low and the reactions ceased. What was cooked in those moments is still with us, unchanged. Every breath you take is 3/4 hydrogen, a direct inheritance of those few minutes, flavoured with the helium that makes stars shine. It is striking to think that all of us carry the imprint of this recipe, Your body is mostly water, and water is 2 parts hydrogen. That hydrogen is primordial, untouched since the first minutes. Every sip you take is flavoured by the oldest ingredient in the cosmos. Helium fills children's balloons, and that helium was also forged then, long before Earth existed, long before stars or galaxies. When you see a balloon floating upward, it is lifted by atoms that have drifted for nearly 14 billion years from the universe's first recipe. Big Bang nucleosynthesis is also a kind of clock. The precise amounts of helium, deuterium and lithium depend on how fast the universe expanded, on how many neutrinos drifted unseen through space, on the balance of protons to neutrons. By comparing prediction with observation, cosmologists can test whether their model of expansion is correct. And indeed, the match has been striking. It is as if the recipe book of the cosmos has been opened, and the handwriting is clear. But the picture is not only one of precision, it is one of poetry. In less than 20 minutes of cosmic time, the raw energy of the universe was transformed into the first stable structures, the first nuclei that could endure. It is easy to overlook this, since we often think of stars as the great forgers of elements, and they are. But before stars, before galaxies, before light itself moved freely, the cosmos in its infancy already wrote the first lines of chemistry. If you close your eyes, perhaps you can imagine the silence of that kitchen. No pots clanging, no flames roaring, only the quiet settling of a recipe being followed by the fabric of space itself. A brief burst of nuclear cooking, and then the fire went out. The result was a mixture so simple and so universal that everything else we know, every planet and person, would depend on it. And so from the quark soup and the breath of inflation, we arrive at a broth flavoured with hydrogen and helium, with tiny pinches of deuterium and lithium. The cosmos had set its table. It would take hundreds of thousands of years before light could travel freely, and hundreds of millions more before stars would blaze, but the ingredients were already in place, quietly floating, waiting to be used again. For hundreds of thousands of years after the Big Bang, the universe was not the clear starry expanse we imagine when we step outside at night. It was a fog, a thick plasma where light could not travel freely. Photons, the particles of light, were caught in an endless dance with electrons scattering again and again like travellers unable to find their way through a crowded street. The cosmos glowed brilliantly, but the glow was trapped, imprisoned in the dense soup of particles. It was a universe filled with light, yet without the freedom of sight. This fog lasted until the universe was about 380,000 years old. By then, expansion had stretched space and cooled the plasma to the point where electrons could finally settle down into stable orbits around nuclei, forming neutral atoms. This process is known as recombination, though the name is a bit misleading. These particles had never been combined before. For the first time, hydrogen and helium atoms became whole, and the electrons stopped wandering. With the electrons captured, the photons no longer scattered constantly. They were set free. The moment of freedom was transformative. Light that had been caged could finally travel unimpeded across space. This released glow is what we now observe as the cosmic microwave background, or CMB. It is not a single beam of light, but a bath that fills every corner of the sky. Even now, billions of years later, it surrounds us, stretched by expansion into faint microwaves. If your television is tuned between channels, a small fraction of the static you hear comes from this ancient glow, a whisper from the universe's childhood. The CMB is extraordinary not only because it exists, but because of its perfection. It is almost a flawless black-body spectrum, corresponding to a temperature of 2.7 Kelvin, just a few degrees above absolute zero. Everywhere we look, it is the same, smooth, uniform, calm. Yet hidden in this smoothness are tiny variations, fluctuations at the level of 1 part in 100,000. These are the echoes of the seeds laid down during inflation. the slight differences in density that would one day guide matter into galaxies and voids. To understand what these ripples mean, it helps to imagine sound. Before recombination, the plasma of the universe behaved like a fluid, and pressure waves travelled through it, acoustic waves, rippling through space itself. Imagine dropping a stone into a pond and watching concentric ripples spread outward. In the early universe, gravity pulled matter inward, while pressure pushed back, and the result was oscillations, like a drum being struck. When recombination occurred, those oscillations froze, captured in the distribution of matter and in the pattern of the CMB. They remain visible today as acoustic peaks, faint but measurable, like frozen ripples in a pond suddenly turned to glass. This frozen music is one of the great treasures of cosmology. By studying the precise pattern of the CMB ripples, scientists have learned the age of the universe, the proportions of dark matter and dark energy, the geometry of space itself. All of this encoded in the faint glow of ancient light still drifting toward us. The CMB is sometimes called the baby picture of the universe, and the name is apt. It is the earliest snapshot we can see, a portrait taken just after the fog lifted. From that portrait, we can trace the features of everything that followed. And yet, despite its precision, there is poetry in the thought that we are bathed in this ancient glow every moment of our lives. It streams through your room as you lie awake at night. It passes through your body as you walk under the sun. It fills every radio dish that listens to the sky. You're living inside a glow released almost 14 billion years ago, a glow that has not gone out. It is worth pausing to reflect on how strange this is. The CMB is not light from a single place, like the rays of the sun or the beams of distant stars. It comes from every direction at once, because it is the fossil light of the entire universe becoming transparent. To look into it is not to look at a point in space, but to look back in time. Every photon of the CMB has been travelling for billions of years, without scattering, carrying with it the memory of the moment atoms first formed. When you gaze at the CMB through the eyes of science, you're looking at a wall of time, beyond which the universe is hidden. This wall is sometimes called the surface of last scattering, and it represents the limit of our direct vision. Beyond it, the universe was opaque. We can infer what happened then through theory and experiment, but we cannot see it directly. The CMB is the oldest light, the boundary of the observable universe's childhood. It is a horizon not of space, but of memory. To bring this down to something everyday, imagine being in a foggy room filled with smoke. At first, you cannot see more than an inch in front of your face, as every photon of light bounces endlessly. But then, suddenly, the smoke clears. The room is revealed, and light from every corner reaches you. That was recombination, the moment the fog of the cosmos cleared, and the light has never stopped travelling since. There is something deeply comforting in this thought. The light of the CMB does not fade because there is nothing left to scatter it, nothing to interrupt its journey. It has been moving calm and steady for billions of years. It is a reminder that even in a universe so vast and uncertain, some signals endure, carrying with them a message from the beginning. Tonight, as you rest, that light will pass through you, just as it has for every creature that ever lived, just as it will for every creature yet to come. When the fog of the early universe finally lifted and the cosmic microwave background began its long journey across space, the universe entered what is often called the Dark Ages. The light was free, yes, but there were no stars yet to shine, no galaxies to sparkle against the darkness. Matter drifted silently. Atoms of hydrogen and helium scattered like dust across a vast expanding stage. It was a universe of potential, quiet and dim, waiting for the first sparks to flare. These dark ages lasted for hundreds of millions of years, but they were not empty. In the invisible background, dark matter had already begun to play its quiet role. Though unseen, it was essential. Dark matter clumped under its own gravity, forming halos, invisible scaffolding upon which the visible universe would be built. Ordinary matter, drawn by gravity into those halos, began to collect and cool. Slowly, almost shyly, the first knots of matter condensed. From these knots, the very first stars were born. They are known as Population 3 stars, a name that sounds clinical but hides their romance. These stars were different from any that exist today, made only of hydrogen and helium, without heavier elements to help them cool and fragment. They grew enormous. Some were hundreds of times the mass of our Sun, brilliant and fierce. They lived fast and died young, burning through their fuel in just a few million years compared to the billions that stars like our Sun enjoy. Imagine the darkness of the universe as a vast, silent plain at night. For hundreds of millions of years, there was no fire on that plain, no camp to guide the traveller. Then, one by one, campfires began to appear. The first stars blazed, scattering light across the cosmic fields. Each fire altered its surroundings, ionizing the gas, pushing back the shadows. Soon the plain was dotted with campfires, clusters of light that would become the first galaxies. The ignition of these first stars ended the cosmic dark ages. It was a turning point, a cosmic dawn. Their ultraviolet light reionized the hydrogen around them, transforming the intergalactic medium from neutral atoms back into a glowing plasma. This process, called reionization, gradually lifted the veil, making the universe transparent not only to ancient microwave photons, but also to new starlight. The night sky as we know it, with light scattered across countless galaxies, was beginning to form. The first stars also had another role. They were the forgers of heavier elements. In their cores, nuclear fusion built carbon, oxygen, and nitrogen, elements that had not existed before. When these giant stars died, many collapsed into black holes, but some exploded in supernovae, scattering their new elements across the cosmos. Those explosions seeded the universe with the ingredients for future stars, for planets, and eventually for life. Every atom of carbon in your body, every atom of oxygen in the air you breathe, was born in those ancient stellar deaths. It is almost poetic to think that the first stars were both creators and destroyers. They lit up the darkness, then died spectacularly, leaving behind not only black holes but also the building blocks of future worlds. Their brief lives were sacrifices that allowed everything familiar to us to exist. Without them, there would be no rocky planets, no oceans, no trees, no people to wonder about their story. Astronomers have yet to observe these first stars directly. They were too faint and too far, their light stretched by billions of years of expansion. But their signatures are written in the chemistry of later generations. When we see stars today with almost no heavy elements, we are peering at descendants of that first era, fossils of cosmic dawn. Soon, telescopes like the James Webb Space Telescope may capture hints of galaxies forming in that ancient time, revealing how the first campfires bloomed across the plain. If you want to picture it more personally, think of walking through a quiet field just before sunrise. The world is dark, hushed, but full of expectancy. Then, on the horizon, the first streaks of light appear. They are small at first, but they change everything. Shadows soften, the outlines of trees become visible, and the day begins. That is what the first stars did for the universe. They ended the long night, and from their fires the story of galaxies, planets, and people began. The cosmic dark ages were not wasted time. They were the settling, the cooling, the quiet before the symphony. And when the music started, it began with the roar of massive stars blazing into existence. It is humbling to realize how brief their lives were compared to ours, yet how profound their legacy remains. Each of us carries in our bodies the ashes of those first fires. Each of us is, in a literal sense, starlight that learned to breathe. And so, the first stars ignited not only the cosmos, but also the possibility of meaning. Their light scattered across the universe, their death seeded it with elements, and their memory lives on in every galaxy and every atom of life. They were the first storytellers, and we are listening still. If you were to step outside tonight and look up at the sky, you might feel that you're seeing everything there is. The stars above, the galaxies scattered across the black canvas, the planets and moons hidden in their silent orbits. All of it seems so vast, so complete, that it is tempting to imagine the universe as a stage already filled with its actors. Yet the truth is stranger and softer. What we see is not the whole performance, but only a faint glow from the edges of a much larger hidden set. The visible universe is only a fraction of what is truly out there, a thin sliver of the cosmic budget. For decades, astronomers have carefully measured the composition of the cosmos, adding up the contributions from everything they can detect. The answer that emerges is both precise and unsettling. All of the ordinary matter, the atoms that make up stars, planets, oceans, forests, and even the breath you're taking right now, amounts to less than 5% of the universe. 5%. Imagine walking into a grand hall filled with furniture and realizing that with your eyes you can only see the smallest corner of one table while the rest is cloaked in darkness. That is our position in the cosmos. The next portion of the inventory, about a quarter of the universe, belongs to something invisible called dark matter. It does not shine, it does not absorb, it does not emit light of any kind. You cannot hold it in your hand or detect it with your eyes, and yet its presence is undeniable. Galaxies spin too quickly to be held together by visible stars alone. Without dark matter's gravity, their outer arms would fling themselves into the void. The way galaxies bend light through gravitational lensing reveals masses far greater than what we can see. In the dramatic collision of galaxy clusters known as the bullet cluster, matter and light separate, leaving behind clear evidence of invisible mass. Dark matter is like the furniture in a pitch-black room. You cannot see it, but you can feel its presence when you stumble against it. What then is dark matter? That remains one of the great mysteries. It may be made of undiscovered particles, perhaps weakly interacting massive particles, or something stranger still. Experiments buried deep underground, shielded from noise and radiation, wait patiently for a signal. So far they have found only silence. But the silence is not empty. It is filled with the weight of dark matter holding galaxies together, guiding their dance across the cosmic web. Without it, the large-scale structure of the universe, the filaments, clusters, and vast voids would not exist. And then, overshadowing even dark matter, comes dark energy. This is the largest share of the cosmic pie, nearly 70% of everything. Unlike dark matter, which clumps and pulls, dark energy acts in the opposite way. It pushes, driving the accelerated expansion of the universe. First discovered in 1998 through the study of distant supernovae, dark energy has since been confirmed in multiple ways. It is as though the universe, rather than slowing down with age, has instead decided to stretch ever faster, pulled by invisible hands. The nature of dark energy is even more elusive than that of dark matter. Some theories suggest it is the energy of the vacuum itself, a cosmological constant built into the fabric of space. Others imagine a new kind of field, slowly evolving with time. Whatever its form, it dominates the universe, quietly dictating its future. If its influence continues unchanged, galaxies will drift farther apart until the night sky becomes empty of everything but the stars of our own galaxy. The cosmic inventory, then, is humbling. Ordinary matter, the kind we touch, the kind that forms mountains and rivers, the kind that writes poems and sings songs, is the tiniest ingredient. Most of the universe is hidden from us, either invisible mass or invisible energy. We live in a universe where the unseen outweighs the seen by 20 to 1, and yet there is comfort in this realization. The mystery is not chaos, it is structure beyond our sight. Dark matter holds galaxies together, cradling the stars. Dark energy sculpts the expansion, setting the stage for all future stories. They are quiet forces, subtle and patient, but without them the cosmos would be unrecognizable. Think of sitting in a dim room where only a candle flickers. Around you, shadows suggest the presence of chairs and shelves, though you cannot make them out. You can feel them if you reach, and the room is shaped by their presence even if you do not see them directly. That is the position of humanity in the universe. Our candle is the visible matter, the stars and galaxies we observe. But the vast room of reality is filled with shapes we are only beginning to sense. The inventory is not an endpoint, but a beginning. Each piece of evidence, the spin of galaxies, the bending of light, the glow of supernovae, reminds us that the universe is more generous, more intricate than we first believed. Dark matter and dark energy may sound forbidding, but they are simply labels for puzzles waiting to be solved. And within those puzzles lies the possibility of new discoveries as transformative as the recognition of atoms themselves. So the next time you look up at the stars, remember that you are seeing not the whole, but the tip of the iceberg, the visible skin of a far greater body. You are part of the 5%, shaped and sustained by forces you cannot see. The universe has hidden most of itself, but it has also left clues everywhere. To walk through the cosmos is to feel the invisible hands guiding your steps, the quiet weight of matter unseen, and the soft push of energy too delicate to name. For a long time, scientists believed the expansion of the universe was slowing down. It was a natural thought. Imagine tossing a ball into the air. Gravity always pulls it back, slowing its rise before bringing it down. In the same way, after the Big Bang had thrown galaxies outward, it seemed obvious that gravity, with its universal pull, would gradually slow the expansion. The universe, everyone thought, might one day halt and collapse back in on itself, or perhaps coast forever at an ever-decreasing pace. But in 1998, astronomers studying distant exploding stars, type Ia supernovae, brilliant beacons that burn with predictable brightness, found something astonishing. The galaxies hosting those supernovae were not merely drifting away at a steady pace, they were accelerating. The farther away they were, the faster they receded. The universe, instead of slowing under the weight of its own matter, was speeding up, as if pushed by some unseen hand. This discovery shook cosmology. 3 independent teams confirmed it, and the scientists involved were awarded the Nobel Prize in Physics in 2011. Since then, ever larger datasets have reinforced the finding, including the Pantheon Plus compilation, which contains over 1,000 supernova measurements. Together they tell the same story. Expansion is accelerating, and something we call dark energy is responsible. The name dark energy is as much an admission of ignorance as it is a description. We know what it does, but we do not know what it is. It appears to be smooth, uniform, and constant across space, exerting a gentle repulsive pressure. Unlike matter, it does not clump or gather. Instead, it is woven evenly into the fabric of space itself. As the universe expands, more space is created, and with it more dark energy. The effect compounds, like interest accumulating invisibly in a cosmic bank account. One possibility is that dark energy is simply the energy of empty space, a cosmological constant represented by the Greek letter lambda. This idea goes back to Einstein himself, who once introduced lambda to keep the universe static, only to later abandon it when Hubble discovered expansion. Ironically, the cosmological constant has returned, now as the leading explanation for acceleration. vacuum energy is real. Quantum field theory tells us that even in a perfect vacuum, particles flicker in and out of existence, and these fluctuations carry energy. But there is a problem, one of the greatest in all of physics. When theorists calculate the expected amount of vacuum energy, the answer comes out not a little too large, but catastrophically wrong. About 120 orders of magnitude larger than what is observed. To put that in perspective, it is like predicting the weight of a feather, and instead finding a mountain range. This mismatch is sometimes called the worst prediction in the history of science. Yet despite its absurdity, the observation remains. The universe accelerates, and some form of dark energy is responsible. Perhaps it is vacuum energy, tamed by mechanisms we do not yet understand. Perhaps it's a new kind of field, dynamic rather than constant, slowly evolving with cosmic time. Perhaps it is something stranger, a sign that our understanding of gravity itself needs revision. Dark energy is quiet, but it is powerful. Imagine placing a feather on one side of a balance scale and a mountain of stone on the other. You would expect the mountain to dominate, but somehow the feather tips the scale. That is the situation in the cosmos. Dark energy is delicate, almost invisible, yet it outweighs the combined pull of all matter, visible and dark. Its influence extends not only across space but into the future. If dark energy remains constant, galaxies beyond our local group will drift farther away until their light is lost to us, red-shifted beyond detection. Over unimaginable timescales, the night sky will empty, and the Milky Way will be an island adrift in darkness. This is the quiet hand of dark energy, stretching the cosmos until even memory itself seems to fade. But here, in this moment, it is worth pausing to consider the paradox. We live at a time when the evidence of acceleration is visible, when galaxies still crowd the sky, when the cosmic web still sparkles with clusters. Billions of years from now, astronomers may no longer be able to measure what we can measure today. They will see only a static sky, unaware that they are adrift in an expanding sea. Our time is uniquely privileged, a window where the universe reveals its secrets before it quietly erases the evidence. Dark energy, then, is not just a puzzle of physics, but also a reminder of perspective. We are small, fragile creatures, yet we live at a moment when the cosmos shares its story with us. That story is written not only in the glow of the cosmic microwave background, or the motion of galaxies, but in the subtle acceleration of space itself. It is a whisper so soft that it took thousands of years of human curiosity to hear it, but once heard, it changes everything. So tonight, as you breathe and listen, remember that space itself is expanding around you. Not quickly, not in a way you could feel, but gently, relentlessly, pushed by a force we cannot yet name. You're part of that expansion, carried outward on currents that began long before your life and will continue long after. The quiet hands of dark energy cradle you as they cradle every galaxy in a universe still unfolding. When you step outside on a quiet night and look up at the stars, you might notice how uneven the sky seems. There are bright constellations clustered here, faint smudges of the Milky Way there, and patches of darkness in between. If you imagine flying outward into space, perhaps it feels natural to picture the universe as patchy and lopsided, a great irregular quilt sewn together from scraps. Yet one of the most profound realizations in modern cosmology is that, when viewed on the grandest scales, the universe smooths itself out. This principle is called the cosmological principle, and it is surprisingly simple. On the largest scales, the universe is both homogeneous and isotropic. Homogeneous means it has the same overall composition no matter where you look. Isotropic means it looks the same in every direction. Up close, there are galaxies, clusters, and voids, but step back far enough, hundreds of millions of light years, and the differences dissolve. The cosmos becomes like a mist. every handful is similar, no matter where you scoop. This assumption has guided cosmology for over a century. Without it, the equations that describe the universe's expansion would be far more tangled. Yet it is not only a convenient simplification, it is also strongly supported by observation. The clearest evidence comes from the cosmic microwave background, that faint afterglow released when the universe was only 380,000 years old. Satellite missions, like COBE, WMAP and Planck, have mapped it across the entire sky pixel by pixel. The result is astonishing. The CMB is uniform to 1 part in 100,000. Imagine a wall painted so evenly that only the most sensitive instruments could detect the faintest brushstrokes. That is our universe. The tiny deviations in that otherwise smooth background are important. They are the seeds of structure, the bumps that later grew into galaxies and clusters. But the smoothness itself is the deeper truth. The universe at its birth was balanced, not favouring one direction over another. It is as though an artist laid down a canvas of nearly perfect white, with just enough texture for patterns to later emerge. You can think of it like wallpaper covering a vast room. From a distance, the surface looks flat and featureless. Step closer, and you might notice subtle imperfections, tiny bumps, a wrinkle here or there. Those imperfections catch the light differently and over time become the anchors for decoration. The cosmic wallpaper is much the same, almost perfectly smooth, yet sprinkled with tiny variations that gravity later amplified into the galaxies we see today. The cosmological principle has been tested in other ways as well. Surveys of galaxies across billions of light years confirm that, when averaged over large scales, their distribution evens out. The Sloan Digital Sky Survey, mapping over 1 million galaxies, shows the same pattern. Zoom in, and you see filaments and clusters, like a sponge. Zoom out far enough, and it blends into a nearly uniform fog. Of course, nature always whispers exceptions. Some researchers have suggested hints of large-scale anomalies, alignments in the CMB that seem to prefer certain directions, or structures like the Giant Arc, a span of galaxies stretching billions of light years. Are these real cracks in the cosmological principle, or statistical flukes born of chance? The debate continues, but so far the principle holds firm. The universe, as far as we can tell, is unbiased, smooth, and democratic on the largest scales. It is worth reflecting on how comforting this is. Imagine if the cosmos truly were lopsided, denser in one direction, thinner in another. The laws of physics might change depending on where you looked. Stars might behave differently in one region of the sky than in another. Planets in distant galaxies might never form because the local balance of forces is skewed. Instead, we live in a universe where the same rules apply everywhere. Hydrogen behaves the same in galaxies 10 billion light years away as it does in the flame of a candle in your kitchen. Light bends the same way around a star on the far side of the cosmos as it does around the sun. The constancy is quiet, but profound, and yet, even within that constancy, there is a lesson about perspective. From our human vantage point, we see unevenness everywhere. The Earth itself is full of mountains, valleys, storms, and oceans. The sky above shows stars clustered and scattered, never uniform to our eyes. Only by stepping far back, mentally, mathematically, and imaginatively, can we glimpse the underlying smoothness. The cosmological principle is not obvious, but once revealed, it is like realizing that what looked chaotic was really part of a larger order. Think of standing in a meadow filled with tall grass. Up close, each blade leans its own way, bent by the wind. The patch near your feet looks different from the patch farther away. But if you could rise high above the field, the details would blend into one sweeping texture of green. The cosmological principle is much the same. On human scales, the universe looks uneven. On cosmic scales, it is smooth. This smoothness is not only a philosophical comfort, it is also practical. It allows cosmologists to model the universe with elegance, reducing the infinite complexity of countless galaxies into a handful of parameters. It lets Einstein's equations sing more clearly, and it ensures that when we look outward, we're not seeing chaos but harmony, tiny ripples on an otherwise calm sea. So the next time you look up and notice how irregular the stars seem, remember that you are standing inside the fine detail of a much smoother story. You're part of the bumps in the wallpaper, the wrinkles in the cosmic field. But above all, you are part of a universe that, at its heart, is even, balanced, and quietly symmetrical. That calmness, stretched across billions of light years, is one of the reasons the cosmos is a place where galaxies could grow, stars could shine, and life could one day wonder why the night sky looks the same wherever you turn. If you have ever tried to measure something in the dark, you know how difficult it can be without a ruler or a fixed point of reference. You reach out your hand trying to guess the length of a table or the height of a chair, and your sense of scale shifts and wavers. Now imagine trying to measure the size of the universe, a space so vast that no physical ruler could possibly stretch across it. For centuries, astronomers were trapped in that same dilemma. They could see the stars, the galaxies, the faint smudges of light at the edges of vision, but they had no reliable yardstick to mark the distances, and yet slowly and patiently the cosmos itself has revealed its own rulers. Two of them, in particular, stand out as the great measuring tools of modern cosmology. Supernovae, which act like cosmic lanterns that fade in a predictable way, and baryon acoustic oscillations which serve as a frozen yardstick imprinted into the distribution of galaxies. Together they allow scientists to map the scale of the universe and track its expansion with astonishing precision. Let's begin with supernovae. Among the many ways a star can end its life, one of the most dramatic is the Type 1a supernova. This occurs when a white dwarf star, a dense ember left over from a sun-like star, pulls matter from a companion until it reaches a critical mass and undergoes a runaway explosion. These explosions shine with such predictable brightness that they can be used as standard candles. Imagine having a collection of identical light bulbs scattered across a dark landscape. No matter where they are placed, you know how bright each bulb should appear up close. If one appears dimmer, it is not weaker. It is simply farther away. Astronomers have used these standard candles to measure distances to galaxies billions of light years away. By comparing the apparent brightness of the supernova with its known intrinsic brightness, they can calculate how far the light has travelled. This method became the key to discovering not only the scale of the cosmos, but also its accelerating expansion, the fingerprint of dark energy we reflected upon earlier. But the universe has given us more than lanterns. It has also given us a ruler, written in sound. In the first few 100,000 years after the Big Bang, the universe was a hot plasma of photons and particles, tightly coupled like a thick soup. In that plasma, sound waves rippled outward, compressing and rarefying matter in great spherical shells. These ripples, called baryon acoustic oscillations, eventually froze in place when the universe cooled and atoms formed, locking the pattern into the distribution of matter. Billions of years later, we can still see the echo of those frozen ripples in the way galaxies cluster. On average, galaxies are slightly more likely to be separated by a distance of about 500 million light years, a faint memory of the sound waves from the early universe. This regular spacing serves as a cosmic yardstick, allowing astronomers to measure distances across vast scales. Imagine tapping a drum in a room and the vibrations leaving a subtle pattern on the dust that settles on the floor. Even long after the sound fades, the arrangement of dust reveals the rhythm that once shook the room. BAO are the cosmic version of that pattern. Modern surveys such as the Sloan Digital Sky Survey, EBOS, and DESI have mapped millions of galaxies, carefully charting these ripples across space. Each survey adds new dots to the grand map of the universe, tracing the web of filaments, voids, and clusters. The ripples are not obvious to the naked eye, but when the statistics are gathered, the signal emerges clearly, like a melody hidden in the noise. BAO, combined with supernovae, give cosmologists two complementary rulers, one from the fading light of dying stars and one from the fossilized sound waves of the infant universe. With these rulers, cosmology has become a precise science. The expansion rate of the universe can be measured not just in broad strokes but with decimal points. Distances to galaxies can be calibrated across billions of light years. The story of acceleration, of dark energy, of the universe's fate is anchored in these tools. Without them, our understanding would drift like a ship without landmarks on a foggy sea. And yet there is something poetic in the way these rulers are given to us. One is born of death, the death of stars, explosions so bright they can outshine entire galaxies for a short time. The other is born of birth, the sound waves of the universe's first light, imprinted forever in the cosmic fabric. Death and birth, fire and sound, explosions and ripples, both turned into steady guides for our understanding. If you think of the universe as a vast dark hall, then supernovae are the lanterns placed along the walls, fading with distance but always with a predictable glow, and BAO are the tiles on the floor, arranged in repeating patterns, giving a rhythm and scale to the hall itself. Together they allow us to walk through the darkness with confidence, knowing that each step can be measured, each direction mapped. So the next time you see a star, remember that some stars, when they die, leave behind more than ashes. They leave behind cosmic light posts that illuminate the universe. And when you hear a faint echo in a quiet room, remember that the universe, too, once rang with sound, and that echo is still etched into the galaxies above your head. The cosmos has given us its rulers not in cold numbers, but in beauty, the fading of light and the freezing of sound, guiding us through the immeasurable night. Science is often described as a steady march toward truth, a line moving cleanly forward with each discovery. But the reality is softer and more human than that. Science is more like a dance. 2 steps forward, 1 step to the side. Sometimes a pause, sometimes a contradiction that forces us to listen more carefully. And in cosmology, perhaps the most striking contradiction today lies in what we call the Hubble tension. The Hubble constant is the number that tells us how fast the universe is expanding at this very moment. It is named after Edwin Hubble, who in the 1920s first measured the recession of galaxies and revealed that the universe was not static but stretching. For nearly a century, astronomers have refined this measurement, hoping to pin it down with more and more accuracy. But as instruments improved, something unexpected happened. 2 beautifully precise methods of measuring the expansion began to disagree, not by a little, but by enough that it matters deeply. One method looks at the early universe. The Planck satellite has mapped the cosmic microwave background in exquisite detail, allowing cosmologists to infer the expansion rate by fitting it to the lambda CDM model, the framework where dark matter and dark energy shape the cosmos. This method produces a value of about 67 kilometers per second per megaparsec. In simpler terms, for every 3.26 million light years, galaxies recede about 67 kilometers per second faster. The other method looks at the local universe, at galaxies and supernovae whose distances are calibrated through a careful chain of measurements called the cosmic distance ladder. Observatories like the Hubble Space Telescope and now the James Webb Space Telescope have sharpened these measurements. They yield a value closer to 73 kilometers per second per megaparsec. Both methods are incredibly precise, yet they disagree. It is as though you own 2 beautifully crafted clocks, both ticking smoothly, both reliable on their own, but when compared side by side, one always runs a few minutes faster than the other. This disagreement is not something that can be waved away by error bars. Each side has checked and rechecked its methods, and the tension has only grown stronger as the data has improved. If the early universe and the late universe give different answers about expansion, then perhaps the universe is whispering that our model is incomplete. Maybe dark energy is not constant but evolves with time. Maybe there is a hidden particle species, sometimes nicknamed dark radiation, that played a role in the early universe. Or maybe gravity itself behaves differently on cosmic scales than Einstein's equations predict. The Hubble tension is not the only subtle strain in the story. There are also puzzles in how galaxies form at small scales. Simulations that include dark matter predict many more small satellite galaxies around big galaxies, like the Milky Way, than we actually observe. This is called the missing satellites problem. There are also disagreements about the density profiles of dark matter in galaxy centres, the cusp core problem. Observation suggests smoother cores, while theory often predicts sharp cusps. These may be details, but they remind us that even with a grand, successful model, there are places where reality tugs against the framework. Some tensions, of course, may eventually dissolve under the light of new data. Others may reveal cracks through which a deeper theory shines. That is the beauty of science. It thrives on tension. Every disagreement is an invitation to look again, to refine, to imagine something new. In this way, the cosmos is less like a closed book and more like an ongoing conversation, with pauses, contradictions, and revisions. And perhaps there is something comforting in this. If the universe gave up all its secrets neatly, the story would be short and quiet, like a song with only one verse. Instead, it is full of variations, refrains, and unresolved chords. The Hubble tension is one of those chords, discordant, puzzling, yet rich with possibility. Think of it like listening to two musicians playing the same melody on different instruments. One plays just a little faster than the other. The notes overlap, but the rhythms diverge. The tension that results is not merely a mistake. It can be the beginning of harmony if understood in the right way. Cosmology is listening now, ears tuned, waiting to hear whether this is a flaw in the performance or a hidden harmony revealing itself. For you, drifting here tonight, what matters is not the numbers themselves, 67 or 73, but the feeling behind them, the feeling that even at the height of precision, the universe retains mystery. That mystery is not a wall but a doorway. It means there is more to learn, more to explore, more stories waiting in the darkness between galaxies. So let your mind rest in that thought. The cosmos is not finished. Its tale is still unfolding, and the very tensions we discover are not failures, but gentle reminders that we are part of something larger than certainty, larger than clarity, larger even than the sky we see. Science, like the universe it studies, is alive, stretching, changing, and sometimes disagreeing with itself in ways that make the future richer. When you think of the word inflation, you might picture something earthly. Prices rising, balloons swelling, or air filling a tire. In cosmology, inflation carries a similar sense of sudden growth, but on a scale that stretches the imagination beyond comfort. Inflation refers to a moment, a heartbeat of time at the very dawn of everything, when the universe is thought to have expanded faster than even light itself, not because anything moved through space too quickly, but because space itself swelled at a speed that outran any signal. Why propose such a wild idea? The story begins with puzzles. Astronomers looking at the universe noticed something strange. The horizon problem was the first. When we look at the cosmic microwave background, the glow left from the early universe, we see light that comes from regions so far apart they should never have been able to exchange information. Imagine two people standing on opposite sides of a frozen lake, each lighting a fire. If the lake freezes before they have time to meet or send warmth across, their fires should look very different. And yet the cosmic glow is astonishingly uniform. as though every patch of sky agreed on its temperature before the light was released. Inflation solves this by saying that, before the rapid expansion, all parts of the universe were once close enough to share warmth, like neighbours at the same fire before being pulled apart in an instant. Then there was the flatness problem. The universe appears to be geometrically flat, like a sheet of paper stretched endlessly, with no noticeable curvature. This is not what we might expect. Left to itself, the universe could have been curved inward like a sphere or outward like a saddle. Inflation solves this neatly. Just as blowing up a balloon makes its surface look flatter to an ant walking across it, inflating the universe smooths out any curvature until it is indistinguishable from flat. And there was also the monopole problem. Some theories predicted exotic magnetic particles called monopoles should have been common in the early universe. Yet we do not see them. Inflation offers an explanation. The rapid expansion diluted them into near invisibility, like spreading a few grains of salt across an entire ocean. So inflation was not invented on a whim. It was designed to solve puzzles that otherwise sat like stubborn knots in cosmology's tapestry, and it did more than untangle them. Inflation predicted that tiny quantum jitters, fluctuations at the smallest scales, would be stretched by the expansion into the seeds of galaxies and clusters. This meant that the very structure of the universe, the cosmic web of filaments and voids, was written in whispers of quantum uncertainty, magnified across unimaginable distances. Observations have supported this picture. The spectral index of fluctuations, which describes how their strength changes with scale, has been measured by satellites like Planck to be around 0.97 close to, but not exactly, the scale invariant 1.0 that inflation predicted. This slight tilt matches the expectations of inflation, strengthening its case. The fluctuations are also nearly Gaussian, meaning they follow the familiar bell-shaped curve, just as the theory suggested. And yet, as with so many elegant ideas, puzzles remain. One question is about fine-tuning. For inflation to work, the field driving it, the inflaton, must have just the right properties, balanced delicately like a ball resting on a slope that is steep enough to roll, but gentle enough not to crash. Why should nature choose such a field? Was it luck, or something deeper? Another issue is the Transplanckian problem. Inflation stretches quantum fluctuations that may have originated at scales smaller than the Planck length, where our current understanding of physics breaks down. How can we trust predictions from realms where our equations cannot see? It is like trying to trace the path of ripples that may have begun smaller than the grains of sand at the bottom of a pond. There is also the question of eternal inflation. Some models suggest inflation does not end everywhere at once. Instead, while it ends in some regions, spawning pocket universes like ours, it continues in others, creating an endless multiverse. In this vision, a universe is one bubble among countless others, each potentially with different laws of physics, floating in a sea of inflating space. It is a profound and unsettling thought that the cosmos we see may be only one small balloon among many rising silently into a limitless sky. But here we must be gentle. The multiverse is a whisper, not a proven fact. It is born from the mathematics of inflation, but evidence remains elusive. Some physicists embrace it as natural, while others caution that it may be beyond the reach of science. It is an idea to hold lightly, like a dream remembered in fragments. For now, inflation stands as one of the great successes of modern cosmology. It explains the smoothness of the cosmic background, the flatness of space, the absence of exotic relics, and the origin of structure. It is woven into the standard model of cosmology with quiet confidence. And yet it is also a reminder that even the strongest theories have edges where the fabric frays. Think of inflation as a breath, a single, swift, silent breath at the dawn of time. That breath smoothed the wrinkles, set the rhythm, and planted the seeds. Without it, the sky might look very different, perhaps too jagged. too uneven for galaxies and stars to form. With it, the universe became a stage where light could shine and life could one day wonder about its beginnings. So as you rest here tonight, picture that moment not as a bang, but as a soft exhalation, a swelling of space so fast and so complete that it set the tone for everything to follow. Inflation is both a solution and a mystery, a triumph and a puzzle, a reminder that in the story of the universe, clarity and enigma often arrive hand in hand. The story we usually tell about the universe begins with a singular beginning, the Big Bang, a hot, dense state from which everything expanded and cooled. But there is another way to imagine it, one that feels less like a single opening act and more like a cycle, a rhythm, a breathing of the cosmos itself. Instead of a one-time explosion, what if the universe bounced? A bounce means that what we call the Big Bang might not have been the true beginning, but a turning point. The universe could have been contracting before it expanded. It might have shrunken to a minimum size and then rebounded, like a ball that hits the ground and rises again. To us, looking back only as far as our instruments allow, it looks like a beginning. But from another perspective, it might have been only one phase in an endless sequence. Physicists have explored several variations of this idea. One of the most imaginative is called the ekpyrotic model. The word comes from the Greek for conflagration, and in this picture the universe's birth is not a bang, but the collision of higher dimensional brains, vast sheets or membranes floating in a higher dimensional space. When these brains touch, the energy released could create a hot, expanding universe like ours. It is as though two invisible curtains brush together in a space we cannot see, and their meeting set the stage for everything we know. Other models lean on the simpler image of a cosmic cycle. Expansion and contraction could alternate forever, like a cosmic heartbeat. Each cycle might smooth out irregularities and seed the conditions for the next. The famous mathematician and physicist Roger Penrose proposed something called conformal cyclic cosmology, or CCC for short. In his vision, each aeon of the universe eventually thins out as galaxies evaporate, black holes fade and only radiation remains. That extremely stretched empty state can, through a kind of mathematical transformation, be thought of as the dense state of the next eon. Thus, the end of one universe is the beginning of another, not with a bang, but with a seamless handoff. There is a poetic elegance in these alternatives. They spare us the unsettling, singularity, the mathematical wall where general relativity breaks down and our equations cannot see further. In a bouncing or cyclic model, there is no sharp edge of time, no absolute beginning. The universe simply moves through seasons, spring following winter, summer giving way to autumn, the cycle repeating. But of course, there are challenges. Inflation, for all its puzzles, has been remarkably successful at matching observations of the cosmic microwave background and the large-scale distribution of galaxies. Bounce models must do the same. They need to explain why the universe is so smooth, so flat, and why the seeds of structure look the way they do. Some versions struggle to produce the right kind of fluctuations, or to avoid instabilities that would unravel them before they can grow. Still, even if they are not the mainstream view, these ideas are valuable. They remind us that science thrives not only on what is confirmed, but also on what is imagined. The very act of proposing a bounce stretches our thinking, forces us to ask why we believe in one beginning instead of many, and keeps the edges of cosmology alive with creative possibility. For the listener tonight, what matters is not the technical details of brain collisions or conformal mappings, but the feeling that the universe may be richer than a single origin story. Perhaps time itself is not a line with a start, but a circle with no end. Perhaps the cosmos breathes in and out, expands and contracts, like the tides of a vast ocean. And if that is the case, then the moment we call the beginning is only one crest in a rhythm that has always been. Picture for a moment a forest in spring. Buds appear, blossoms open, leaves unfurl. To an observer who knows only that moment, it might feel like the first and only time, but we know that winter preceded it, and autumn will follow, and that the cycle is endless. A bouncing universe is a cosmic forest, always returning, always renewing, never truly starting or ending. And there is a kind of comfort in that. If the universe bounced before, it may bounce again. Our cosmos may be one verse in a longer song, one note in a melody that plays across aeons. Inflation gives us a swift breath, a smoothing at the start. Bouncing gives us a rhythm, a reassurance that even when everything collapses, there can be renewal. Neither story is complete, neither story final. Both are invitations to wonder. And in that wonder lies the beauty of cosmology, not just in the measurements and equations, but in the way they open our minds to possibilities as vast as the night sky. So as you close your eyes tonight, you might imagine yourself not at the end of a straight path, but standing in a circle. Around you, the seasons of the cosmos turn, springs of creation, summers of light, winters of collapse, and then new springs again. The stars above you are not just ancient, they may be eternal companions in an endless dance of birth and rebirth. Time equals 2 seconds. When most of us think about the speed of light, we imagine it as the ultimate limit. Einstein's theory of relativity built a universe where light speed is not just fast but sacred, woven into the very structure of space-time itself. It is the law that nothing outruns. And yet, in the long halls of cosmology, there are whispers of ideas that dare to bend even this rule. They are not mainstream, not universally embraced, but they are part of the creative dreaming that keeps science alive. One of those whispers is the idea of a variable speed of light. At first, the notion sounds almost rebellious. If light speed is constant, how could it ever change? But cosmologists who proposed this were not trying to defy Einstein for the sake of it. They were trying to solve the same puzzles that led others to inflation. Why the universe looks so smooth across vast distances, why it is so flat, why relics like magnetic monopoles are missing. If in the early universe light travelled faster than it does now, then distant regions could have communicated before drifting apart. Horizons could have been bridged, irregularities smoothed, problems resolved without the need for inflation. The idea is bold, but it also comes with deep questions. How would the laws of physics look if light speed could change? What else would have to shift to keep the universe consistent? Masses, charges, the strength of forces. It is like pulling on a single thread of a sweater and watching the whole garment reshape itself. A variable speed of light theory is not impossible, but it asks us to rewrite much of the structure we take for granted. Alongside VSL, there are other speculative pictures. One is string gas cosmology, which emerges from attempts to link the early universe with string theory. In this vision, the cosmos began not as a hot, smooth field, but as a dense tangle of vibrating strings. These strings, fundamental objects in the theory, can wind around extra dimensions. Some dimensions grow large, unfolding into the space we live in, while others remain curled up too small to see. In this view, the properties of the universe, the number of dimensions, the kind of particles that exist, arise from the way strings choose to settle and vibrate. There is something strangely poetic about it. Instead of a universe born in a bang, we might picture a universe emerging from music, from vibrations at the tiniest scale, strings humming in silence, weaving geometry and matter into being. The song they play may have infinite verses, most of which are hidden from us, but its echoes are written in the structure of the cosmos. These speculative models are not widely accepted in the way inflation is, but they are valuable in a quieter way. They expand the landscape of ideas. They test what might be possible. They remind us that science is not only about confirming what is already solid, but also about sketching on the margins, exploring drafts that may never make it. to the final page. In fact, most of physics is like this. Behind every polished theory are dozens of abandoned sketches, ideas that were tried, tested, and set aside, yet each of them nudged understanding forward in its own way. Think of it like an artist's notebook. The finished painting hangs on the wall, admired for its clarity, but in the studio the notebook is filled with half-drawn figures, colour experiments, and strokes that never quite worked. Those unfinished sketches are not failures. They are part of the process, necessary steps toward what eventually endures. Cosmology is no different. Inflation may be the polished painting, but VSL, Stringus models, and other wild proposals are the sketches in the margins showing the breadth of human imagination. And there is comfort in knowing that the universe encourages such dreaming. If the cosmos is vast and strange enough to contain galaxies by the trillions, then surely it is also vast enough to contain our attempts to imagine beyond the limits. Most of these ideas will not survive the hard light of observation, but even if they fade, they leave behind a trace, a reminder that we're not only measuring but also daring, reaching beyond the obvious. For you, listening tonight, it may not matter whether light once travelled faster or whether strings wound themselves around dimensions we cannot see. What matters is the gentle realization that science is not rigid, not closed, but alive. It breathes with questions. It tolerates experiments in thought, even the ones that never settle. That is how progress happens, through a mix of structure and play, rigour and wonder. So as you settle into rest, picture the universe as a book, but not one finished and bound. It is more like a draft, pages scribbled with notes, margins filled with sketches, some crossed out, some circled in hope. Inflation may be the strong central chapter, but around it there are side notes. What if light was faster? What if strings hummed the first notes of being? What if cycles replaced beginnings? These questions are not distractions. They are reminders that knowledge grows not in a straight line, but in many directions at once, like branches reaching toward the light. And perhaps that is the softest truth of all, that even as we seek the solid, we must also keep space for the uncertain. For in that uncertainty, imagination flowers, and from imagination, new paths to understanding may one day emerge. When you stand on a beach and look out across the water, the horizon feels like a boundary, a line where the sea meets the sky, a place that looks so definite yet forever stays out of reach. You can walk toward it, or sail for days, but the line will always retreat. It isn't a wall, it's a limit born of perspective. Cosmology has its own horizons, and like the ocean's edge, they tell us both how far we can see and how far we can ever hope to know. The first of these is called the particle horizon. It is the maximum distance from which light has had time to reach us since the beginning of the universe. Imagine turning on a lantern in a dark field and waiting for light to spread. The longer you wait, the farther the glow travels. Our universe has been glowing for about 13.8 billion years, but because space has been expanding during that time, the light that reaches us today actually comes from regions now tens of billions of light years away. That's why cosmologists say the observable universe is about 46 billion light years in radius. Beyond that lies more universe, possibly infinite, but hidden from us because its light has not yet had time to arrive. The particle horizon is like the outer edge of a lantern circle, soft, not absolute, but real. There is another horizon, more sobering, the event horizon of the universe. Unlike the particle horizon, which grows as time passes, the event horizon is a limit set by the universe's acceleration. Because dark energy drives space to expand faster and faster, there are galaxies whose light, even if emitted today, will never reach us. The distance between us and them grows too quickly for light to close the gap. In that sense, the event horizon is like a shoreline receding as you try to swim toward it, always moving away, always just out of reach. this leads to a bittersweet thought. For now, the night sky is rich with galaxies, clusters, filaments of light woven into a grand cosmic web. But in the far future, most of those galaxies will slip beyond our event horizon. Their light will fade from view, not because they cease to exist, but because the accelerating fabric of space carried them away faster than light could follow. To future astronomers, if any remain billions of years from now, the sky may appear nearly empty. The universe's story, so expansive in our eyes, will close in on them like a narrowing window. It is a quiet irony that we, here and now, live at a privileged moment. We can still see galaxies billions of light years away. We can measure the faint afterglow of the Big Bang. We can trace cosmic structures across immense scales. In the distant future, all of this evidence will vanish from sight. The universe will hide its past more carefully, leaving only local stars or perhaps none at all to whisper of its origins. It means that, without realizing it, we exist in a cosmic dawn, when the night sky is fullest, when the evidence of creation is still spread before us like open pages. The metaphor of horizons reminds us that knowledge itself has boundaries. There are things we cannot know, not because we are uncurious, but because the universe is structured that way. No telescope can outpace the speed of light. No experiment can pull galaxies back across the event horizon. There will always be mysteries that remain beyond reach, and yet, that limitation does not feel harsh. It feels human. To have edges is part of what it means to be alive in a finite world. Think of standing on that beach again. You cannot reach the horizon, but that doesn't make the ocean less beautiful. In fact, the horizon may be part of what makes the view so moving. It invites the imagination. Beyond it might be islands, currents, storms, or calm seas, but you cannot see them, and that's fine. The horizon's very distance enriches the mystery of what lies beyond. In the same way, the cosmic horizons frame our understanding. They tell us, this is what we can know, and beyond that lies wonder. It is humbling, but it is also liberating. It means the universe is not exhausted by our measurements. There will always be more, hidden, receding, waiting. So tonight, as you drift into rest, you might imagine yourself sailing across a cosmic sea. The stars are lanterns on distant shores, the galaxies like islands far away. Around you, the horizon stretches in all directions, curving, elusive, eternal. You will never reach it, but you don't need to. It is enough to sail, to watch, to know that even in the vastness, you are part of the story that unfolds between the visible and the hidden. The edges of the knowable are not an end. They are a quiet invitation to wonder. Every story eventually asks the same question: how will it end? The universe itself, vast and ancient, is no exception. We can look back billions of years to the Big Bang, trace the formation of stars and galaxies, and measure the expansion that carries them apart. From this, cosmologists try to peer forward, not with certainty but with possibilities. The ultimate fate of the cosmos depends on the mysterious dark energy that now drives expansion. Will it continue as it is, grow stronger, or change course altogether? Each path leads to a different ending, and though the universe may last for trillions upon trillions of years, its storylines can be told now, softly, like lullabies of futures that may never come. The first and most widely favoured scenario is called heat death, sometimes called the Big Freeze. In this vision, the expansion of the universe continues forever. Galaxies drift farther apart and stars one by one exhaust their fuel. The night sky slowly loses its brilliance as stars fade into white dwarfs, neutron stars and black holes. Even black holes in unimaginable spans of time evaporate through Hawking radiation. What remains is a thin mist of particles and photons, stretched and cooled until the universe hovers close to absolute zero. It is not a sudden end, but a long dimming. like a candle burning lower and lower, flickering gently before going dark. The story does not close with a bang, but with a whisper. Another possibility is the far more dramatic Big Rip. This occurs if dark energy is not a constant, but grows stronger over time. In that case, acceleration would not just separate galaxies, but would eventually pull apart clusters, then galaxies, then solar systems, then planets. In the final instance, even atoms could be torn apart as the very fabric of space-time accelerates beyond cohesion. It is a violent ending, like a violin string pulled tighter and tighter until it snaps. The cosmos itself unravels, not into silence, but into shreds. Yet even here, there is something strangely awe-inspiring. The image of a universe so restless that it cannot hold together, so full of drive that it ends by scattering everything it contained. There is also the possibility of a big crunch. This is the mirror image of expansion. If for some reason dark energy reverses or proves unstable, gravity might eventually overcome acceleration. Galaxies would slow, then begin to draw together. The universe would contract, growing hotter and denser, until all matter collapsed back into a single fiery state. In that moment, it could resemble the conditions of the Big Bang. Some versions of cosmology even imagine that from such a crunch, a new universe might be born, leading into a cycle of bangs and crunches without end. It is the image of a pendulum swinging back and forth. Expansion, collapse, expansion again. The end of one universe becomes the beginning of another. Each of these possibilities rests on what dark energy truly is, and at present we do not know. It may be a cosmological constant, steady and unchanging, pointing us toward heat death. It may be dynamic, shifting over time, opening doors to rips or crunches. Or it may be something we have not yet imagined, a form of physics still waiting to be uncovered. In that sense, when we speak of cosmic futures, we are telling stories, informed by data but infused with imagination. The future is not written. It is a horizon still out of reach. For you listening tonight, it may feel strange to think of endings so immense, spanning timescales beyond comprehension. But perhaps there is comfort in knowing that whatever happens, it will not be sudden. Stars will shine for billions of years yet. Galaxies will spin. The universe will carry on long after our tiny lives have passed. These endings are not threats, but quiet projections, reminders that we are part of something both fragile and enduring. And maybe the most soothing thought of all is that whatever the ultimate fate, the present moment remains luminous. We live in a universe where stars still burn, where galaxies still glow, where the sky at night is scattered with light. The ending may be dark, or loud, or cyclical, but now, tonight, the universe sings with brightness. It is this chapter we inhabit, and this chapter is enough. So as you rest, imagine the futures as gentle metaphors. A candle burning lower until only smoke remains. A string snapping in sudden silence. A pendulum returning to its still point, ready perhaps to swing again. These are not dooms, but lullabies, ways of framing the universe's long story as a rhythm. A song that carries on even when one verse is done. In the end, perhaps it does not matter which scenario comes true. What matters is that we are here now, able to imagine, able to gaze at the stars and wonder how their story will unfold. To hold endings in mind while living in the middle is a kind of balance, a way of honouring the cosmic tale without rushing toward its close. The universe is vast, the future's many, and tonight, all you need to do is listen to its quiet possibilities. When people first hear the words Big Bang, the image that comes to mind is usually something loud and fiery. Fireworks in the sky, sparks flying outward from a single point, fragments racing away through empty space. It feels natural to imagine it that way, because that is how every explosion we know behaves. A balloon pops, a star shell bursts, a firecracker fills the air with a light. But the beginning of our universe was not an explosion in space. It was something stranger, something more subtle, and in its quiet way, something far more beautiful. Imagine for a moment a balloon lying flat. On its surface, you draw a few small dots. Now, as you blow air into the balloon, it stretches. The dots move farther and farther apart, yet none of them are racing across the surface on their own. They stay where they are, but the space between them grows. That is closer to what cosmologists mean when they speak of the universe expanding. Galaxies are like the dots, fixed in their own neighbourhoods, while the balloon's surface, space itself, stretches and carries them apart. Another way to picture it is with bread dough rising in the oven. Sprinkle raisins in a lump of dough. As the dough expands, the raisins move away from each other. No raisin is shooting off like a bullet. They are simply passengers in a loaf that is swelling larger. The Big Bang was not the raisins being flung outward by an explosion. It was the dough expanding, space itself growing, carrying everything within it along for the ride. This is why it is misleading to think of the Big Bang as fireworks. There was no empty space into which the universe exploded. Space itself is what began stretching. There was no outside, no black void around the explosion. The Big Bang did not happen at one point in the universe. It happened everywhere, all at once, because space itself was involved. If you trace the history backward, every point in space was once closer to every other, until you reach the hot, dense beginning. The bang was not a bang at all, but a rapid expansion of everything everywhere. It also helps to think carefully about the idea of speed. When we say galaxies are moving away from us, it sounds like they're flying through space. But on cosmic scales, what is really happening is that space between galaxies is stretching. This can even make galaxies appear to recede faster than light, and at first that seems to break a rule. Nothing, after all, is supposed to move faster than light, but the rule applies to things moving through space, not to space itself expanding. Just as the surface of the balloon can expand as quickly as it likes, the universe itself can stretch at any rate, carrying galaxies with it. Light speed still holds true locally. Nothing overtakes a photon in its own neighbourhood, but globally, distances can increase faster than light can close them. It is not a violation, just a reminder that our everyday images of motion don't quite fit cosmic reality. This difference explains why we sometimes see galaxies moving toward us, even though the general rule is expansion. The Andromeda Galaxy, for example, is on a slow collision course with the Milky Way. On small scales, local gravity can tug objects together, overcoming expansion. The raisins in the bread can still bump into each other, but on the grand scale, across billions of light years, the loaf itself continues to swell. The Big Bang, then, was not an explosion that filled space with matter. It was space itself filling with expansion. That is why cosmologists often prefer gentler metaphors. Not fireworks, but a balloon slowly inflating. Not shrapnel in the air, but raisins in rising dough. It was the growth of a stage, not the scattering of its actors. This shift in perspective is important because it changes how we feel about our place in the universe. If it had been a simple explosion, we might imagine a centre, a location where the blast began. We could picture ourselves at some distance from it, like bystanders after a firework display. But in an expanding universe, there is no centre. Every galaxy sees itself at the middle, with all others moving away. From the point of view of any observer, the universe expands around them. You're not at the edge of the blast. You're part of the stretching itself. It also softens the word bang, which was always a bit misleading. There may have been an unimaginably hot, dense state, but there was no crack of sound in the surrounding silence. There was no shock wave. The laws of physics as we know them unfolded quietly, space stretching, particles forming, light beginning its long journey. If there was a sound, it would not be like thunder. It would be more like a low, deep hum, the resonance of a universe beginning to breathe. And so the Big Bang is not best pictured as a violent detonation, but as the first breath of space itself, a breath that carried galaxies outward, that stretched light waves into the gentle glow of the cosmic microwave background, that continues today in the quiet, steady expansion of the night sky. As you rest tonight, you might think of the universe not as a firework fading into darkness, but as a balloon still slowly rising, or a loaf of bread filling with warmth as it expands. You're not outside it, watching from a safe distance. You're part of it, carried with the galaxies, woven into the very fabric of the expansion. The Big Bang was not an explosion. It was the soft beginning of space, still unfolding, still carrying us gently outward. When you listen to music, you notice that the pitch of a note depends not only on the instrument but also on how it is played. Stretch a string tighter and the note rises. Loosen it and the sound deepens. Imagine now that the universe itself is like an enormous instrument, stretching over time. As it expands, the light travelling through it is drawn out, stretched into longer and gentler wavelengths. What once was bright and blue becomes soft and red. This stretching of light is what astronomers call redshift, and it is one of the most direct pieces of evidence we have that the universe is growing. At first glance, it is tempting to think of redshift as something familiar, like the way an ambulance siren changes pitch as it drives past you. The sound waves are compressed as the ambulance approaches and stretched as it moves away. Light can behave in a similar way, which is why astronomers sometimes describe a galaxy's redshift as a kind of cosmic Doppler effect. In this view, the galaxies are racing through space, their motion shifting the colour of their light just as a siren's motion shifts the sound. But in truth, the reality is gentler and stranger. On cosmic scales, galaxies are not moving away from us through space in the ordinary sense. Instead, it is space itself that is stretching, carrying the light with it. The waves of light as they travel are pulled longer, like taffy being stretched by invisible hands. This is called metric expansion, not a chase through space, but the growth of space itself. To picture it, think of an accordion being opened slowly. The folds pull apart, and any sound moving within it is drawn out into deeper notes. Or imagine painting a wave across a rubber sheet, then stretching the sheet. The wave becomes longer, its crests farther apart, even though nothing is moving across the sheet. That is what happens to starlight on its long journey across the universe. It leaves its galaxy at one wavelength and arrives at ours with that wavelength lengthened, softened, as if time itself has sighed and let it drift into red. This distinction between Doppler motion and metric expansion may seem subtle, but it changes how we think about the cosmos. If galaxies were merely moving away through pre-existing space, there might be a true centre, a special place from which the expansion began. But because it is space itself stretching, every observer, everywhere, sees the same effect. From Earth, we watch galaxies recede, but an observer on a distant planet would see us receding just the same. No one stands at the middle. Everyone is carried outward equally, like passengers on a raft that is inflating beneath them. Redshift also explains why the night sky carries messages from the past in such a softened tone. The light from the most distant galaxies is not just faint, it is stretched so far into the red that our eyes cannot see it at all. Only with radio telescopes and infrared detectors can we capture these whispers. They arrive like old songs played at half speed, their notes slowed, their voices deepened. The universe is not silent. It is filled with echoes of light shifted gently toward the red. And then there is the most famous redshift of all, the cosmic microwave background. This faint glow began as searing light from the young universe, hot and white. But over billions of years, the stretching of space drew those waves longer and longer until they became microwaves, invisible to human eyes yet detectable with sensitive instruments. What we measure now at 2.7 Kelvin, the cold afterglow that fills all of space, is simply the same original light, stretched by time and distance into a softer key. The song of the beginning still plays, just tuned down to a whisper. For a moment, think of yourself lying in bed while an old record plays in another room. The door is closed, the walls muffled, but you still hear the rhythm slowed and softened. That is what it is like to detect redshifted light. We are listening through distance and time, the music slowed, but the melody still there. Understanding redshift is also how astronomers measure distance. The greater the redshift, the farther the galaxy. It is like looking at a set of candles, each giving off the same flame, but the farther ones appear dimmer and redder through the fog. By measuring that stretch in wavelength, scientists can map the universe, building a three-dimensional atlas of space. It is through redshift that we discovered the expansion itself, and it is through redshift that we found the acceleration, the signature of dark energy hidden in the data. Yet despite its central role in cosmology, redshift is not a violent process. Nothing is torn, nothing is lost. The light stretches quietly, almost tenderly, as if the universe were humming it into a lower octave. The galaxies do not feel themselves racing away. They sit in their clusters, spinning and forming stars, unaware that their light is being softened as it journeys across billions of years. Tonight, as you close your eyes, you might imagine the light from a distant galaxy beginning its path billions of years ago. It travels patiently, crossing voids, skimming past clusters, always moving forward. By the time it reaches you, its colour has shifted, its song lowered, but its story intact. In that softened glow is written the history of the universe's expansion, a record of time's long stretch. The redshift is not just a technical detail, it is a reminder that the universe itself has a rhythm, a breath. Every photon is stretched as the cosmos grows, carrying in its lengthened waves the memory of a universe that is always expanding. It is not the shout of an explosion, but the soft sigh of space unfolding. When you hear the word nothing, you probably imagine a kind of blankness, an empty room with no furniture, a stretch of sky with no clouds, a desert where the sand lies flat and still. In everyday life, nothingness is the absence of all things, a space with no contents at all. For centuries, people thought of the vacuum in that way, simply a void, a background stage that holds no actors. But in the quiet depths of physics, nothing turns out to be surprisingly busy. What we call empty space is not truly empty. Even when you remove all particles, all dust, all light, the quantum fields that underpin reality cannot help but tremble. This restless energy of the vacuum is known as zero-point energy, and it means that the vacuum is never fully still. Like a pond that ripples ever so faintly even when no stone has been thrown, the quantum vacuum hums with fluctuations. These fluctuations are not just theoretical whispers, they can be measured. One of the most famous demonstrations is called the Casimir effect. Imagine placing two metal plates very close together, separated by only a hair's width. Quantum fluctuations exist all around, but between the plates only certain wavelengths can fit. The result is that the plates feel a gentle push toward each other, as though invisible hands were pressing them together. It is not magic, but the subtle influence of the vacuum itself, quietly nudging matter. This is one of the profound lessons of quantum theory. Even silence is not silent. Even emptiness is not empty. A vacuum is more like a stage humming with hidden music, a background where notes rise and fall, even when no instruments are playing. Physicists describe these tremors as virtual particles, pairs of particle and antiparticle that flicker briefly into being and then vanish. They are not permanent residents of reality, but fleeting guests, appearing and disappearing too quickly to be directly seen, yet leaving fingerprints on the physics we observe. And here lies one of the boldest ideas in cosmology. Perhaps our universe itself emerged from such a fluctuation. Some scientists propose that if quantum uncertainty allows virtual particles to flicker in and out, then on rare occasions perhaps entire universes can do the same. The role of gravity in this story is crucial. Normally, creating matter and energy would require immense cost. But gravity, with its peculiar ability to contribute negative energy, can balance the books. A universe filled with galaxies and stars might still add up to zero when you combine matter's positive energy with gravity's negative pull. Out of nothing, you could have a cosmos, provided the laws of physics themselves already exist to allow the fluctuation. This is, of course, speculative. It does not answer the deepest question: why should there be laws at all? Or why should there be a quantum vacuum in the first place? But it suggests that the leap from nothing to something may not be as impossible as it first sounds. Instead of a miraculous event, it could be a natural process, the kind of fluctuation that quantum fields cannot help but produce, magnified into cosmic scale. Philosophers sometimes raise a quiet objection here. They point out that when physicists say nothing, they often mean quantum vacuum, which is already a kind of something. It has structure, laws, properties, and ability to fluctuate. True nothing, in the purest sense, may not even be something we can describe. It may not exist within the bounds of science at all, and so the question, why is there something rather than nothing, remains, resting in the delicate border between physics and philosophy. Still, even if the full answer eludes us, the image of the vacuum as a seething, humming backdrop can be a comforting one. It tells us that silence is never absolute. Beneath every pause there is always a whisper. Beneath every stillness there is always motion too subtle for our eyes, like hearing the faint hum of a refrigerator in a quiet kitchen, or the murmur of wind even on a seemingly still night. We are reminded that the universe never truly rests. This restless background also shapes our present-day universe. It may be connected to the mysterious dark energy that drives cosmic acceleration. It certainly shapes the behavior of particles and fields in the smallest realms. It reminds us that what we call empty space is one of the richest and strangest fabrics imaginable, woven with vibrations that sustain reality itself. Tonight, as you lie in the quiet of your room, you may think you're surrounded by stillness. Yet even here, in the air and the space between atoms, fields are trembling. Vacuum energy is humming. Silence is humming with hidden notes. Nothing is never really nothing. The same quiet tremor that might one day have sparked our universe is still here, surrounding you, invisible but ceaseless. Perhaps that is one of the most calming thoughts. The universe began not with a violent explosion into void, but with a whisper rising out of the hidden hum of the vacuum. Out of the quiet, something bloomed, and that bloom continues, carrying galaxies, carrying stars, carrying you. In most of our everyday maps, the world feels continuous. A road leads to a village. The village connects to fields. Fields meet rivers. Rivers reach the sea. Even if the terrain changes, you can follow one place to another without falling off the edge. But physics, when it is pressed to its limits, shows us something stranger. It shows us points where the map stops. These are called singularities, places where our equations break down, where gravity curves space so tightly that numbers slip away into infinities, and where we are left staring at blank corners of the cosmic chart. The most famous singularities live at two extremes of our universe. One is at the very beginning, the Big Bang, the moment our known history starts. The other is deep inside black holes, the mysterious hearts of collapsed stars. In both cases, general relativity, the brilliant theory of gravity that Einstein gave us, predicts that density becomes infinite, curvature unbounded, and the very fabric of space-time curls into something it cannot describe, yet infinity is less a physical object than a signal, a red flag waving at us from the frontier. It says, here, the laws you're using are not enough. Take the Big Bang. According to relativity, if you trace the expansion backward, galaxies and stars draw closer and closer, until everything converges into a single point of infinite density about 13.8 billion years ago. But most physicists believe this point is not a real thing, not an actual pinprick of impossible density, but a symptom that our theory is missing something. We need a framework that can merge gravity, which rules the very large, with quantum mechanics, which rules the very small. We need quantum gravity, a language in which both the curve of space-time and the jitter of particles can be spoken together. Now consider black holes. At their centres, relativity predicts singularities where all matter is crushed into zero volume, creating infinite density again. Yet here too infinity whispers more of our ignorance than of reality. Black holes test the limits of physics, and they raise puzzles that touch not only gravity, but also information itself. Stephen Hawking famously showed that black holes are not perfectly black. Through a subtle interplay of quantum fluctuations near the event horizon, they can emit radiation. This so-called Hawking radiation means that black holes might evaporate slowly over unimaginable spans of time. But if they vanish completely, what happens to the information about everything that fell inside? This is the information paradox, the clash between quantum mechanics, which insists information is never destroyed, and general relativity, which seems to suggest that black holes erase it. It is as though two great orchestras are playing side by side, each following its own sheet of music, and when they meet at the edge of a black hole, their scores no longer match. One must be incomplete, or both must be rewritten into a grander harmony. That grander harmony is what physicists hope a theory of quantum gravity will be. Many candidates have been proposed: string theory, loop quantum gravity, causal sets, and others. Each attempts to smooth out the infinities, to replace singular points with something more structured. In string theory, the basic units are not points but vibrating strings, and these can spread out the sharp infinities into softer finite values. In loop quantum gravity, space itself is quantized into tiny chunks, so that curvature cannot collapse infinitely but hits a smaller scale. None of these ideas is yet confirmed, but they all share the goal of replacing blank spaces on our map with new terrain. For now, though, we must live with the limits. The Big Bang singularity stands as the edge of our cosmic story. We can tell the tale of what happened after the first instant, but not what happened at or before it. Black hole singularities remind us that even the most robust laws of physics falter when pushed too far. And yet, rather than despair, many scientists take comfort in these mysteries. They are signs not that the universe is broken, but that our understanding is unfinished. Where the map goes blank, new discoveries wait. There is something oddly soothing about this. Imagine sitting by candlelight with an old map of the seas. The coasts of Europe and Africa are drawn carefully, dotted with ports and rivers. The edges of Asia fade into guesses. Beyond that, the parchment is marked with faint drawings of dragons or serpents, warnings of unknown waters. But sailors still set out, carrying the map as far as it would take them, and then sailing beyond, where the paper ended and the sea began. Our physics is much like that. Singularities are our dragons drawn where the math stops, but we keep looking outward, knowing that reality continues even where our equations fail. So tonight, as you let your thoughts drift, consider this. The universe does not give us final answers easily. It offers us mysteries at the boundaries, places where our maps go blank. The Big Bang is not a completed chapter, but the first word blurred. Black holes are not tidy prisons, but riddles that test the rules of information itself. At the edges, our equations break, but the stars still shine. That means the story is not finished. And in that unfinished story lies the promise of wonder, the promise that there is always more to learn, always more to imagine, always more horizon to sail toward. When we look up at the night sky, we often think of stars as cold and distant, their light arriving after thousands or millions of years of travel. but hidden in the orbits of those stars may be small rocky planets, worlds with oceans and weather, places where life could quietly take root. The question of whether the universe can bear life is one of the most human questions we have ever asked, and it is also one of the gentlest. To wonder about life is to wonder about companionship, about whether the great silence of the cosmos is truly empty, or whether it simply speaks too softly for us to hear. Life, at least as we know it, has some modest requirements. It needs water, not in the form of ice or vapour, but liquid water, because water is the solvent that allows molecules to mingle, to bump together, to form the long, delicate chains that make biology possible. Life also needs energy, some steady source of fuel. On Earth, sunlight serves this role, feeding green plants and algae, driving photosynthesis, and filling the oceans with food chains. But energy can come from other sources too. On worlds far from their stars, life could find warmth from chemical reactions or from tidal heating, the push and pull of gravity kneading a planet until it glows faintly inside. An atmosphere helps as well. It can trap warmth, shield a surface from radiation, and create a stable environment where fragile molecules do not break apart instantly. Finally, life requires time. Time for molecules to experiment, to connect, to fail, and to try again. Time for evolution to stumble through countless forms until it finds one that can persist, reproduce, and grow. These are the ingredients, and yet they are not rare in the universe. Water, carbon, energy, and time are spread throughout the cosmos. What seems rare, at least from where we stand, is the right balance. Astronomers have found thousands of exoplanets circling other stars. Some are gas giants like Jupiter, others are hot worlds racing around their suns in just a few days. But nestled among them are rocky planets, some in the so-called habitable zone, where temperatures might allow liquid water to exist. We do not yet know if those worlds actually hold oceans or atmospheres, but they whisper possibilities. Each one is like a small candle flickering in the dark, a reminder that Earth may not be the only hearth in the cosmic night. Closer to home, we have discovered worlds that may carry oceans beneath their icy shells. Europa, one of Jupiter's moons, hides a deep sea under its frozen crust. The ice may crack and shift, warmed from below by tidal forces as Jupiter's gravity pulls and stretches it. Enceladus, a tiny moon of Saturn, sprays geysers of water into space, carrying hints of salts and organic molecules. These hidden oceans, cut off from sunlight, might still harbour warmth and nutrients. They are, in a way, small islands of liquid stability in the cold seas of space. Imagine them as underground caves lit not by sunlight, but by the glow of hydrothermal vents, places where microbes could cling to life, as they do in Earth's deep oceans. It is a soothing thought that life might not be a miracle confined to our blue world, but a pattern the universe writes wherever conditions are right. Life could be hardy, persistent, able to bloom in shadows and under ice, not fragile but surprisingly resilient. On Earth, we find microbes in boiling springs, in acidic lakes, even in rocks miles beneath the surface. They tell us that life does not demand perfection. It only needs a foothold, and once it finds one, it can hold on tightly. And yet, despite all this potential, we have no direct evidence of life beyond Earth. Telescopes search the skies, spacecraft probe planets and moons, rovers crawl across Martian soil, and still we have not found so much as a fossil or a microbe. That silence can feel heavy, but it can also feel like a gentle invitation to keep looking. The universe is vast, and our searchlight has only swept across the smallest corner. Perhaps the cosmos does bear life, but we have not yet reached the shore where it flickers. There is a kind of comfort in imagining that the recipe for life is simple, but the outcome, complex conscious life, may be rare. Perhaps microbes thrive everywhere, hidden in icy oceans or drifting in clouds, but civilizations like ours are scattered thinly, too far apart to notice one another. The night sky might then be full not of absence but of whispers we cannot yet hear. Tiny islands of warmth in a cold sea, waiting quietly. As you rest tonight, you might think of Earth as one such island, a fragile sphere wrapped in its thin shell of air, carrying forests and rivers, carrying you. Beyond us, other islands may be out there, lit softly in the darkness, carrying their own forms of life. Whether they are microbes clinging to vents or creatures staring at their own skies, they are part of the same story. The universe may not only allow life, it may gently encourage it, as though scattered warmth is its way of keeping company across the void. On a summer evening in 1950, the physicist Enrico Fermi was walking to lunch with colleagues in Los Alamos. The conversation had turned, as it sometimes did, to flying saucers and interstellar travel. Fermi, after a moment of silence, suddenly asked the question that still echoes through astronomy today, but where is everybody? In that simple remark lives the puzzle we now call the Fermi Paradox. If the universe is old, if stars are countless, if planets are common, and if life arises easily, then intelligent civilizations should be abundant. Some of them should have reached out, colonized their galaxies, left traces, yet the night sky remains quiet. No signals, no ships, only the vast silence of space. The paradox sharpens when we think in numbers. Our Milky Way has more than 100 billion stars. Even if only a fraction have habitable planets, there should be billions of places where life could emerge. And if intelligence is not impossibly rare, then somewhere, someone should have built radios, telescopes, or spacecraft. Some should have expanded outward, just as humans dream of doing. Given time, even a slow-moving wave of exploration could sweep across a galaxy in a few million years, a blink compared to the billions of years the universe has existed. If so, the question repeats, why is the sky so quiet? There are many answers, and none proven. Perhaps life itself is rare. The ingredients may be common, but the recipe may require an exact sequence of accidents that only Earth experienced. The jump from chemistry to biology, or from microbes to intelligence, may be so improbable that it happens only once in a galaxy, or once in a universe. That possibility paints us as unique, not in a boastful way, but in a fragile one, like a single flower blooming in an otherwise empty field. Or perhaps civilizations do arise, but they do not last. Technology may carry within it seeds of destruction. Nuclear war, ecological collapse, uncontrolled machines. Any of these could end a young species before it learns to reach for the stars. In this view, the quiet sky is a graveyard filled with ruins we cannot yet see. Each silence is a reminder of how delicate survival is, and how precious it is that we endure at all. Another possibility is distance. Even if the galaxy is full of voices, they may be too faint to hear. Imagine standing on a shoreline and calling out. The waves crash, the wind blows, and your voice travels only a short distance before dissolving into the air. Across the ocean, others may be calling too, but their voices never reach you. Our radios and telescopes are small candles against a storm, and perhaps the cosmos is already humming with signals just beyond our range. There is also the possibility of deliberate silence. Perhaps advanced civilizations know we are here but choose not to speak. They may follow a cosmic version of the Prime Directive, letting young worlds grow without interference, or they may see communication as dangerous, preferring to remain hidden. Silence could be a form of caution, or even kindness. To a civilization millions of years ahead of us, our first radio waves may sound like the babbling of children. They may smile and wait for us to grow older. Some scientists suggest that the paradox is not a paradox at all. They argue that with only one example, Earth, we cannot judge probabilities well. The universe is vast and our search has only just begun. We have listened to a fraction of the sky for a fraction of time, like dipping a single cup into the ocean and declaring it empty of fish. In this view, silence is not surprising. It is simply the result of a search just beginning, a child still learning to listen. Projects like Breakthrough, Listen Now scan the heavens with radio telescopes, searching millions of stars for narrowband signals, the kind nature does not make. They may not find anything soon, but even silence is data. Every year we listen, we better understand how rare or common signals may be, and even if we never hear another voice, the act of listening binds us to the cosmos. It reminds us that we are part of a larger story, one that could hold many chapters yet unread. So the quiet sky may not be a disappointment. It may be a canvas, still blank, waiting for us to add our own colours. We're already sending faint signals outward, radio and television shows slipping into interstellar space. Perhaps one day someone will catch the flicker of our presence and wonder about us, just as we wonder about them. Until then, the silence is not emptiness. It is space for imagination, for questions, for awe. As you rest tonight, picture the universe as a great ocean at night. You stand on the shore with a small flashlight sweeping it across the dark waves. The beam is thin, and it touches only a few ripples, leaving the vast waters unseen. Somewhere across that ocean, another traveller may be sweeping their own light, and perhaps someday our beams will cross. Until then, the ocean is quiet but not unfriendly. It waits, calm and patient, holding secrets in its depths. We've wandered far together tonight, farther than any ship or signal could ever travel. We began at the edge of time itself, in that first flash of creation where everything that ever was began to unfold. We drifted through the early haze of the cosmos, watched light escape its first prison in the cosmic microwave background, and saw the first stars spark awake against an ocean of dark. We traced the ingredients of existence: matter, dark matter, and the unseen push of dark energy. And then we turned quietly inward, toward the gentler questions. Where did it all come from, and why does it still go on? And now, before the night closes, we gather those thoughts like a blanket at day's end, folded, still warm, softly complete. Think again of the universe's expansion. It was never an explosion but a stretching, not fragments flung into space, but space itself expanding, like bread rising patiently in a bowl. That gentle growth carries galaxies apart, leaves faint ripples frozen in the microwave sky, and even now pulls distant clusters faster than light can chase. The farther we look, the quieter it becomes. Yet that distance isn't loss, it's rhythm. Like waves receding at low tide, it reminds us that what drifts away still belongs to the same sea. Remember too the quiet partners of creation, dark matter and dark energy. The first is the invisible scaffolding, the hidden structure that holds galaxies in graceful suspension. The second is even subtler, a whisper that urges expansion onward. Both remind us that what shapes reality is often what cannot be seen. Just as love, memory or longing cannot be measured but still guide our lives, these unseen forces shape the universe's fate. We spoke of the astronomers who measure what cannot be touched, building ladders of distance, comparing flickers of light, chasing the faint hum of ancient ripples. Their work is not just mathematics, it's faith, the quiet belief that even mysteries obey rhythm. When their clocks disagree and their rulers falter, it's not failure but invitation, proof that knowledge itself is alive, still moving, still forming. The universe, after all, is not a finished painting. It's a canvas still wet, its colours shifting as we watch. We revisited the idea of inflation, that first impossible breath that stretched everything smoother than silk, planting the seeds of galaxies. It might not be the final answer. Perhaps there are cycles, bounces, shifting light speed, or hidden beginnings we haven't yet imagined. But each of these ideas carries something deeply human, the desire to look back to the very first spark and ask, softly, why? We reach for that mystery like children pressing their hands against frosted glass, unable to see through, yet comforted by the faint glow behind it. We lingered at the edges too, event horizons, cosmic horizons, the far futures of heat and silence. They sound like endings, but perhaps they are pauses or preludes to something new. Even to imagine an end is to affirm that we belong to a story, one with rhythm, rise, and rest. Along the way, we untangled the common misunderstandings. The Big Bang was not an explosion, galaxies are not flying through space, redshift is not merely a chase but a cosmic stretching of song. And with that softer understanding, the universe feels less like a riddle and more like a melody, one we can hum along to, even without knowing every note. Then we reach the gentlest places, the vacuum that hums with invisible energy, the singularities where knowledge folds in on itself, the idea that nothing might simply be a kind of fullness waiting to bloom. These are not voids to fear, but doorways, places where wonder lingers. To know that there are limits is to know that there is always more to discover. Finally, we asked about life, that delicate flicker of warmth scattered across the cold. We imagine oceans beneath alien ice, vents where microbes might cling to heat, signals yet unheard. Perhaps the silence is solitude, or perhaps our listening has only just begun. Maybe other minds are out there, shining their own small lights, their beams not yet crossing ours, and even if not, perhaps the quiet itself is enough. To ask is already to belong. So here, at the edge of thought, let us fold the night gently. The universe may have risen from quantum murmurs or from an eternal cycle. It may fade into heat, collapse into gravity, or breathe again. Life may bloom only once or 1,000 times. Civilizations may pass like sparks. Yet through it all, you are here, a brief consciousness held tenderly by the same cosmos that once kindled the first stars. Whether you're still awake or drifting away, let that be enough. The stars above you tonight are the same ones that saw the first galaxies form, and the same ones that will watch distant worlds rise and fall. The universe is vast beyond reason, and yet, tonight, it rests quietly in your breath. Sleep now, little traveller. You're made of the same whispers that built the galaxies. Rest, and let the universe keep its secrets a little longer. It will still be here when you wake, patient, humming, infinite and kind.